Welcome to APEC. It's October 28th, and I'm your moderator, Tim Ventura. First, I want to thank everybody for joining us on this call, along with everybody watching us on YouTube. We're streaming on StreamYard, so we are across multiple channels. The Alt Propulsion channel is our primary one, but we want to thank everybody on Alien Scientist and on Bernie's channel and on all of the various broadcast streams that we are out across today. So today, Tiziano Fulceri will discuss optics as a fundamental unification paradigm for gravity. Brendan Darrer will provide a detailed analysis of subquantum kinetics. Curtis Horn is going to be talking about Spinor, Quaternion GR Mach Effects. And Isaiah Ritchey will provide an overview of his Searl Effect Generator replication project. All of these are amazing presentations. I'm really, really excited, and I think you guys are going to be as well once we get into things here. We're also going to be hearing updates from our lab partners, and we're going to try and finish off the event with an open discussion by conference attendees. That is a bit later down the road. We have a lot to work through. Let me do a couple of quick updates first, though. Today's event is on StreamYard, as I mentioned earlier. Our primary channel is Alt Propulsion. If you haven't subscribed, please do so now. You can ask questions using the live chat feature on the right-hand side of the page. If you're watching this in replay, you obviously won't be able to do that. But for anybody who is here while we're broadcasting, we see those come right into the studio, and we will try and ask them to the presenters if we have time. You can also view conference replays, details, and speaker info on our website at altpropulsion.com. If you haven't visited there in a while, we have been making updates to it. Again, that is altpropulsion.com. And of course, we always list upcoming events. We have a schedule and a calendar there as well. So without further ado, I want to get into our first presentation. What causes gravity? Sir Isaac Newton discovered and expressed gravity in his equations. Oops, sorry about that. Wrong one. Tiziano Fulceri, optics as a fundamental unification paradigm for gravity. There we go. So optics is understood in the modern sense as the study of propagation of perturbations within a medium, and it stands out as an all-encompassing unifying vision for all branches of fundamental physics, even if the specific details of some regimes aren't worked out yet. This vision can serve as a guide in constructing new specialized theories in quantum gravity. And even in causal microscopic emergent explanation for the perturbation of gravito-inertial fields by masses based on testable, reproducible phenomena. So again, Tiziano Fulceri, I'm going to bring him in now. He has a little bit of delay on his end, but he is here with us. I'm going to unmute him. Tiziano, welcome, sir.
Hello, welcome. Thank you for the introduction.
Absolutely, absolutely.
Absolutely bolder when you recited it and when I wrote it on my blog. But thank you.
Well, so I've got your presentation up, and again, we do have a little bit of a delay, so it may make communication a little bit more challenging. I'm going to take myself out of the stream. I will still be here, so if you have any issues or challenges, just let me know. And take it away, sir. And again, thank you. It is truly a pleasure and an honor to have you present this for us.
Thank you. So if I may start, first, a few words about myself. I come from physics originally. I studied physics at the University of Pisa in Italy. I'm Italian national, and I specialized in plasma physics. The Master's of Science in Plasma Physics at the Technical University of Munich in Germany. During university, in between bachelor and master, and also afterwards, I have always been working with research and development, both in institutions and industry. Dealt with optics, electronics, power electronics, plasma experiments, and software development. I So this is what I do as an official job. Parallel to this, I've always been interested in the fundamentals of physics. So I study the philosophical and historical foundations of physics itself. I like to delve deep into the history of the concepts. I like to read the original papers. So what I will present you tonight is a collection of what I have gathered in these years when I do this systematically. My approach is very conservative in the sense that I try not to invent or not to introduce new strange stuff. I try to work with just what we have in the literature, especially the old literature, which I think is rich with treasures. But let's get on. Okay, so optical unification and gravito-inertial engineering. But what does it mean? What do I mean by that? This is an idea which I came across the beginning of this year, and it's basically using the whole known physics as it is, with the fewest modification possible, and try to see new connections and new interpretation of old battle-tested mathematics and theoretical concept and also experimental evidence. What I will talk about tonight. So this is a brief table of contents. I'll explain why I do this and why this is relevant in particular for the APEC alternative propulsion community. I'll do a little journey along the last 100 years of physics, starting from 1923, exactly, from the proposal of de Broglie to assign wave character to electrons, not only to light. I will explain a little bit what I think about what is now called quantum mechanics, how the wave properties of matter connect with general relativity, and what general relativity is really about, not what following interpretations which are written on the university textbooks say. I will introduce the concept of the space as an electric medium. This is not new. This is also 100 years old stuff. But I will introduce this in a way that connects with the previous things and also with the following. Like, how do we construct a theory in which you have the Lorentz transformation of special relativity, and it all falls down naturally from ordinary wave mechanics that you learn the first semester in physics. I will introduce the concept of matter and light as excitations, so not as objects themselves, but as an excitation of a background thing that I call, and my collaborators also call the substratum or substrate, which is better than the old word ether, because I will explain that later. And then I will explain what I mean by gravito-inertial engineering. Why do I use this strange, with this apparently strange word? And what do I mean by engineering? And then, yes, there will be some conclusion about what we have said tonight. And I will listen to questions, maybe, and comments and feedback, criticism, whatever. This is meant to be a sparring section. So if something which does not convince you, it's good to have discussion. But let's get on. So the motivation for all of this, I think it's very common to all the alternative propulsion people. As a young student in physics back in 2009, I was very interested in exotic, so-called exotic alternative propulsion. So I got myself the book Frontiers of Propulsion Science, which I'm sure you are familiar with, at least the APEC community. It's a very interesting book, which came out of a research program from NASA, the Breakthrough Propulsion Physics program, which identified murky, unclear areas of fundamental physics with big potential for so-called breakthrough. So radical revolutions in understanding of the physics, which could bring new unexpected technology, in particular in the fields of energy and propulsion. Of course, this was done by NASA. They were interested in space propulsion. What do they say? So the final message of this book is that before we even think about modifying gravity, modifying inertia, building flying saucers, strange starships which bend space-time, first of all, we must understand how natural gravity works. What's the physics of it? What's the nature? What's the essence of it? How does matter and light, so energy in general, do what it does? What does it mean that matter and energy bend space-time? Is this even the correct way of understanding this? And from the point of view of the mainstream, we are stuck, because on the one side we have general relativity, which is a classical field theory. On the other side, we have so-called quantum mechanics, which is a recipe of algorithm to be applied to a so-called quantum state to probabilistically predict the outcomes of certain experiments which are implemented in specific experimental setups. So before doing the engineering, before building strange, new, and beautiful machines which can levitate or create gravitational fields, first we must understand how gravity works as it is in natural gravity. This requires a breakthrough and requires a reevaluation of current physics. So this is a starting point. Where do we start? Start from the beginning. So what makes gravity already? We know that matter and light, for what we know. Energy in whatever form. So if it is confined, we call it matter. If it is radiant, we call it light. But it's all really the same. We know it from at least 1905 when Einstein published his famous paper, not the electrodynamics of moving bodies, but the other one, just after, about the content of inertia of a body. Does it depend on the energy? Yes or no? The answer is yes. And the law of transformation for mass and confined energy are exactly the same and are even, they're proportional to each other, and the constant of proportionality is 1/c². What does it mean? It means that anything that you can touch, anything that you can see, planets, stars, people, cars, houses, we know very well that it can be decomposed in elementary particles in the final analysis, but those elementary particles are nothing else than confined energy. Radiant energy, which bunches around or circles around in a small volume. This is what the physics tells us, apart from the formulas. So this is important. This is the most. This is the starting point. We look around. We know the planets make gravity, stars make gravity. They influence the trajectory of light and of other matter. And it seems that the only thing that generates gravity is energy in some form or another, at least the natural version. Starting from here, we keep it on our notebook, and we go further along in this revisit of modern physics. What happens in 1923, exactly 100 years ago? Louis de Broglie, which is a lover of relativity of Einstein, but also a guy which comes from the French tradition of history and mathematics, and also experimental science. He was very good with experiments involving radio frequency and electrons. He was operating as a radio frequency operator during the First World War on the Eiffel Tower. Of course, he was from Paris. French tradition. So by examining the Lorentz transformation and by looking at some strange behaviors in experiments involving electrons, he starts to propose this strange thing that, look, at the beginning of the 20th century, we discovered that light is both wave and particle properties because of Young experiment, because of the photoelectric effect, which was discovered, if I'm not wrong, in the 90s of the 19th century. So already Planck had worked out the quantum. Einstein used that to explain the photoelectric effect itself. So light was not only a wave, but had to be understood also as a stream of particles. De Broglie makes the opposite thing. He says, look, I have a bunch of electrons, and I think that when they go through slits, the bunch of electrons should diffract and should make interference just as light does. So also to the good old solid matter, we have to assign wave properties. And his initial idea, his proposal for a research program was to assign both a particle nature and a wave nature. So it was not a duality. It was really the two things present at the same time. You would have a particle, which is like a very small region of space, which propagates through space, and it has an internal clock, an internal heartbeat, internal cyclic phenomenon. And this particle must be always in phase with an external phase wave, which is an enigmatic thing because it had this superluminal velocity, it had infinite velocity when the particle was still. But anyway, this was a proposal, and it was proposed in this little piece on the right that you see in Nature in the September of 1923. So, and in this little piece, and also in other articles, papers that de Broglie published, he put forward this idea. He said, look, I think that electrons diffract. In fact, it was observed just 1 year later, 2 years later. That means that we cannot just use the old principle of inertia for matter anymore. We have to update it. We have to generalize it, and we have to do to matter what has been done to light. That is going from the geometrical optics, so rays, straight lines, to wave optics. That means you have to take care of the interference that you do when you go through slits, and also the diffractions, that these particles deviating from the straight lines when they go to small enough slits. This, of course, we already know where it led to just 1 year later. But it's interesting to know that this idea of unifying the propagation of solid particles, point particles, and wave phenomena is not new, and it does not come from the 20th century, and does not come from Schrödinger, does not come from de Broglie, neither. It comes from Hamilton, Hamilton and Jacobi, which by the end of the 30s of the 19th century developed the Hamilton-Jacobi theory, which was developed exactly with the purpose in mind to unify the theoretical treatment of propagation of particles and propagation of waves. So you could say that the real kickstarters of the quantum revolution, or the wave particle revolutions, were 100 years older than what we usually think. This is interesting because Hamilton, when he started doing this, he used pre-existing physics in the form of Maupertuis principle for point particle, and in the form of Fermat principle for wave propagation. So he basically unified what was then optics for waves and mechanics, so the propagation of point particles. And he invented exactly what we call now the least action principle, which is the generalization of what we had before for light, combined with what we had before just for matter. And it's interesting because the principle of least action is used everywhere in modern physics, from quantum physics to special relativity theory to general relativity, also to so-called non-fundamental physics in fluid mechanics, electrodynamics, so evolution of electromagnetic fields, it's used everywhere to find the equation of motions, and then of course you solve the equation of motions and you find the trajectories or the evolutions of the field. This is interesting to note because, of course, we know that in 1926 or 1927 stuff went wrong. So there was the Survey Conference, and some other guys, Bohr, Heisenberg, Pauli, took over this idea, which was developed by de Broglie first and Schrödinger, and started to abstractize everything. It is they invented the matrice mechanic, which is now the official default way of presenting so-called quantum mechanics that you get in university in every bachelor course or in physics or master's course if you do physics. So basic quantum mechanics. So you can find in normal textbook like Sakurai, Cohen, Landau, number 3, textbook stuff. Of course, the mathematics works perfectly. It connects with the experimental prediction, but there's a problem. All the mathematics and all the algorithms are a kind of statistical signal analysis, which do not give an account of matter evolving in 3D space over time. And this is a problem. This is a problem because after what is done, 100 years of trying to build a theory of quantum gravity through any means possible, no success was reached. And of course, no success was reached because the problem is not in the mathematics, not how complicated you make your spin networks, your strings, your 26-dimensional theories, your emergent space-time, which is a philosophical absurdity. It's not about that. It's that we live in a 3D world, 3-dimensional world, and things evolve over time. So there are objects which are made of atoms and molecules and particles, and these atoms and molecules and particles live in a 3D world. And they are the ones which generate gravity in virtue of their position and velocity and energy content and mass content and momentum content, and are acted upon by gravity. So from this point of view, what is solved as quantum mechanics nowadays is not a theory which can be used to describe matter, so the structure and function of matter. That's why we have to go one step further. In fact, let's talk about GR for a second. I know it sounds like a jump, but there is a sense in this. GR was developed by Einstein between 1907 and 1915, after the so-called happiest thoughts of his life, when he discovered what he then called the equivalence principle. That is that in his version, that a local gravitational field can be nullified by just falling through it, so that acceleration and a gravitational field can cancel one another. This was the starting point for developing his theory. But the first attempts that he did in 1907 and 1911 at describing how gravity first bends light, and then he also tried matter, but first he tried with light, was by imagining that space itself has a varying index of refraction. And there are attempts in 1907, 1911 of this. Unfortunately, he did not follow through this route because he was missing key information that the differential geometry approach rendered more evident. So he abandoned that road. He contacted his friend Grossman at ETH Zurich and said, please help me, I'm getting crazy. And Grossman provided him with a newly developed absolute differential calculus, which then became the standard way of writing the equation of general relativity. As you can see on the right, that's the paper from Einstein from 1915, where he gives the field equation there in the middle. And then that's it. I mean, this is a classical field theory. It's perfectly legit. The problem is that then interpretations came. The interpretation was that this was geometrizing gravity, and gravity is just geometry, and you just have to think it like a curved geometry of 3+1 pseudo-Riemannian manifold. Therefore, there is no meaning in asking what's the mechanism, how matter does it. Matter is described by quantum physics. Quantum physics does not live in 3D space. It lives in n-dimensional Hilbert space. So this question has no meaning. Fact is that Einstein never believed that general relativity geometrizes gravity. There is a nice paper by Dennis Lemkuhl, philosopher of science, from 10 years ago, where he clearly identifies the quote from Einstein and says, look, this is absurd, because the only thing that means is that we have unified the gravitational and the inertial field. So it's a single field, which I like to call the gravito-inertial field. And he did his analysis, like, look, it's when, like, Maxwell devised the theory for the electromagnetic field. He did not geometrize electricity or magnetism. He just said, look, that electricity and magnetism are two aspects of the same thing. And this is what my theory does. So this is Einstein quoted from Lemkuhl. So we should see general relativity really just like all the other field theories. You have a source of a field, which is connected with the field, then the field interacts with the source. The geometry viewpoint is not the only one. In fact, I argue that it is not tenable anymore because of also other reasons, which I did not put here. But, for example, it has been discovered that you can describe gravity both with torsion and no curvature, or with curvature and no torsion. But then it was also been discovered that gravity can be described with non-metricity alone, or curvature alone, or torsion alone. This is called the trinity of gravity. There are researchers at the theoretical physicists department in ETH Zurich doing this. What does it mean? It means that geometrical description is just one geometrical description. There are possibly infinite ways of interpreting the field equations and the phenomenology itself. Of course, my favorite one is the one which considers the space itself as an electric medium. So this might sound preposterous, like, yeah, of course you can say that light bending is due to a graded index of refraction, but this is an ad-hoc explanation. It makes no sense. It's a post-hoc addition to the true and only geometrical interpretation. But actually, first of all, Einstein himself tried to do it. He didn't succeed because he didn't have the right mathematical skill at the moment. He didn't have the whole picture in mind, and he opted for differential geometry. But very important names, since just after the general relativity was completed, they started to do this. Eddington and say, okay, let's interpret the bending of light as a changing index of refraction. And then Wilson came, 21, and then Dicke, 1957, the year that was the beginning of the renaissance of the general relativity or gravitational physics. But these were all approximate attempts. They were approximate. The first one, which really provided a one-to-one mapping between the curved field, the curved pseudo-Riemannian manifold description, and the flat Minkowski background provided with the electric medium with changing index of refraction, was Plebanski in 1961 in his article Electromagnetic Waves and Gravitational Fields. And then after him, many others in the 60s, in the 70s, in the 80s, in the 90s, going up until really yesterday, they reproposed the same model, but that's it. That there's an isomorphism, there is a one-to-one connection. And I think the most clear way that it was expressed can be found in the article by Ulf Leonard and his collaborator Philbin of 2006. General Relativity in Electrical Engineering. It's open access. Check it out. It's beautiful. It gives you the recipe of how to build a block of material, a dielectric material, which acts on light as space-time does. And you can see down there the recipe. So you give me the metric. I take all the determinant of the metric, the determinant of the space part, the components on, and I can build a material with a tensorial epsilon mu, so permittivity and permeability, which vary together with each other. So you have a, what's it called, impedance matched material, or yeah, that's the name, impedance matched material. So the ratio stays the same. That means that in vacuum, in so-called vacuum, you never have reflections. You can have refraction, but not reflections. And this is there, 2006, and this is used not in the way that we would like to use it to make propulsion, but it's used in the other way around. They take some strange, nice curved geometries, which come from astrophysics or general relativity curve, and they say, okay, how can we make this? How can we make a block of material which directs lights in the way that we want? And they do it. It's called transformation optics. You can do very nice things with it. You can do invisible stuff, cloaking devices, invisible devices. You can even simulate white holes, black holes, all static though. So you build a block of material, and the epsilon mu are fields, are functions of the position, or in general inhomogeneous and anisotropic, but they are not dynamical. They're static. However, this is interesting. This suggests something. So maybe space is something like this, but space is different because it's dynamical. It changes the epsilon mu and W field, the magnetoelectric coupling, are dynamical. They respond to the distribution of matter. I'll come back later to this. Where do we go from here? If space is an electric medium, what about relativity? 1887, Michelson-Morley experiment failed to detect direction-dependent and velocity-dependent variation in the fringe interference pattern of a closed-loop interferometer. What does it mean? They wanted to build a speedometer for matter cruising through the ether, because they supposed that the ether was the medium of which light, and this is important, and only light was an excitation of. So they would imagine some kind of liquid or gaseous material which was very thin, so that matter could just cruise through it and have almost no drag, almost. And light was a wave, an excitation of this. So this was strange because, of course, there was no drag. There was many different experiments similar to Michelson-Morley were tried, but no one could detect a really direction-dependent, velocity-dependent effect. And so people started to investigate why, and then you get Larmor at the end of the beginning of the 20th century, Lorentz, Poincaré, which were already working this since the 19th century. Of course, you have to put in Lorentz contraction, Lorentz Fitzgerald contraction. You have to put it in time dilation, and the last fix that you have to put in by hand is the desynchronization along the direction of motion. So there is this little addition in the time of the Lorentz transformation that transform time into so-called proper time, which all seems very odd and fixed by hand. And everybody was trying to find a so-called constructive explanation for this, constructive in the sense explained by Harvey Brown in his beautiful book, Physical Relativity. That is, I want a bottom-up explanation of why matter contracts when traveling through the ether. And there was some attempts, there was some beautiful insights by people like Fitzgerald, like Heaviside. Heaviside predicted the contraction of matter based on Maxwell equation. But it was the beginning of the 20th century, because 1900, 1902, 1905. And of course, they say, yes, if matter is held together by electrical force, and if electrical force must follow the contraction from Maxwell equation, then yes, you could have a natural contraction of other objects. But nobody understood atoms, intermolecular forces. The microscopic structure of matter was still a matter of opinion. There were people in the 1900s which were still thinking that atoms were a useful hypothesis. Imagine that. And nobody had an idea of the atomic structure, how electrons stay together, how atoms, molecules stay together, why the forces between atoms should be electrical and not something else. So what happens? Albert comes in. Einstein arrives and say, you know what? Let's do this. Let's not do a constructive explanation. I don't know how to do it. We don't know how to do it. We don't know almost anything about the structure of matter. Let's do a principle theory. Let's just say that for every system, I wrote here an opto-electromagneto-mechanical system which moves around, new transformation are valid. Precisely the Lorentz transformation. They're nice, they are symmetric, they form a group, they break distance simultaneity, they make the other undetectable, they make every observer think that they are the center of the universe, that they always think that light travels at the same speed. Everyone thinks this, but it doesn't matter, because you cannot measure one-way speed of light. You can measure only round-trip speed, and the round-trip speed, because of geometry, which is where we'll explain in the book by Franco Selli, weak relativity. Didn't find the English edition cover. So because of geometry, so back and forth speed of light comes always the same. Synchronization for distant clock is arbitrary. Einstein chooses a convention which breaks simultaneity. Then you get what you get: standard special relativity, the electrodynamics of moving bodies, Lorentz symmetry, in the sense of the group symmetry of the transformations. And then you get the geometrization by Minkowski in 1908, in 1909. And also here, everything becomes super abstract and super disconnected from matter, from the systems itself. However, the story was not over. Fortunately, starting from the work of Reichenbach, I think. But I learned this from the article, from the paper of Mansouri and Sexel, 1977. Actually, it's a series of 3 articles dealing with test theories of special relativity. So the theory on how to test the theory of special relativity. Very interesting. What do they come up with is a scheme in which you actually can change the synchronization convention for distant clocks. You don't choose the Einstein convention, which is like always assume that when light goes back and forth or forth and back, takes the same amount of time for the 2 stretches. Abandon this and just say, this is true only if I am at rest with respect to the medium, to the substratum. However, I can never detect such a state of motion. But with this, you do a slight change into the transformation, and you actually can maintain distant simultaneity within a basically Newtonian framework. Stuff which moves through the ether actually slows down, actually contracts along the direction of motions, and actually loses synchronicity along its direction. But it's a local problem. So the clocks or the chronometers are no longer synchronized within the moving system. This does not mean that time itself changes. This is a lot of information. This is very well explained in the book by Harvey Bryan, also by his papers, and he's continuing work on this. This is called the constructive approach, or dynamical physical relativity. So how, just don't philosophize about space and time. Just say, okay, you have moving stuff. Moving stuff is not good for measuring distances and times and synchronization. And of course, this has been accused of neo-Lorentzianism, and Occam razors is coming to cut all of this. But this is not so strange as it seems. I'm almost there. In fact, all of this seeming craziness can be reconciled if one just abandons the unwarranted assumption that the ether is just luminiferous, so bringer of light. It's not only luminiferous, it also, how do you call it? Materiferous. It also brings matter. So both light and matter are an excitation of this substratum. And if you think matter is something like this, then something magical happens, because you can look at infinitely many analog systems, so-called fishbowl universes, as Bouchard describes in his 2008 paper, a real Lorentz Fitzgerald contraction, where you have a block of material, itself obeying Newtonian mechanics. Within this material, there are excitations, so there are waves or wavelets or solitons, that means focused out, self-focusing regions of wiggling, waving, cycling waves, which itself, so for these excitations, which exist only as a state of motion of the substrate, for them the world is Lorentz symmetric. So they experience contraction when they move, they experience time dilation when they move, and they experience desynchronization. This has been proven mathematically, geometrically, for a wide variety of systems. You can build such systems. Analog systems are called, where instead of the c, so instead of the light velocity, light speed in c, you use the sound velocity, and then you get Lorentz symmetry. So it's like Lorentz symmetry is just, it's not even something specific of matter traveling to the ether. It's something that comes out every time that you have things which are made of waves which have a maximum propagation speed. And then you can add another thing to this fishbowl universe, that if the characteristic speed, which is given by the refractive index of the material, slowly changes in different places of the material itself, then you have that the propagation of light, of waves, and also of localized solitons, you may call them, does not follow straight paths. They deviate. And they deviate because they follow the Fermat principle, or the least action principle, if you want to call it that way. And they deviate towards the region where the characteristic speed is lower. If they are just radiant energy, so radiant wave. If they are confined, they fall down towards region. So they accelerate toward regions where the characteristic speed is lower. And this looks a lot like bent space-time. It's completely equivalent. So it's you apply the least action principle to a material which is in general inhomogeneous and anisotropic, and then you have the excitation of this material propagating in paths which are not rectilinear. And by the theorem of Plebanski, you can just say, okay, I just implemented a curved space-time. So the space-time for the excitations, they don't care about the external space, flat space-time in which the material itself is sitting. They just care about the internal simulated spacetime. And this is nice because we're almost there. You have a system where you have internal excitations, which are wave-like, so they connect to wave mechanics. We could say quantum mechanics. It connects, they have the properties of the Lorentz symmetry, which is the properties of our ordinary matter have. And they also follow curve trajectories based on the background changes of the medium in which they propagate. It looks a lot like our own world. So this fishbowl universe, it's really very similar to our world. What is the thing that is missing? The thing that is missing is that the inhomogeneity or the anisotropy of the permeability, permittivity, and magnetoelectric fields are static. They do not depend on the position of the solid in itself. So what do we need to close the circle? We need metamaterials. So if I build this fishbowl universe with metamaterials, with space-time modulated metamaterial, which were discovered really yesterday. So this is a research from the Meta Research Group in Belgium by Professor Callot, which I had contact way beginning of this year. Very interesting. So these are materials where you can actually dynamically edit in real time the effective refractive index. That is, you take a block of material, you excite it with a certain signal, which is not electromagnetic. You can use thermal, you can use mechanical, you can use ultrasound, you can use some external means. This induces a modulation pattern in space and time inside the material, which for propagating electromagnetic disturbances inside the material look like dynamical permittivity, permeability, and magnetoelectric field. So they can mimic one-to-one, perfectly mathematically, geometrically identical gravitational fields. Space-time metrics, which may or may not be solutions of the Einstein field equation. So of course you can mimic a constant acceleration field, you can mimic a black hole, you can mimic a white hole. Here you can see this in the picture. This comes from their work. I'll send you the link if you're interested. And you could say, okay, but this is just a fishbowl universe. This is simulated gravity. I said, yes, but this has been the thinking until now. What I'm proposing here is that the coincidences are too many. What I think is that we really live inside a fishbowl universe. Lorentz symmetry from special relativity is constructive. There is a background ether which is undetectable because the interferometers with which we try to detect it are made of this quasi-matter that propagates as a perturbation inside the material itself. Gravity is just the changing of the characteristic speed of the refractive index of the material. And to close the circle in this analogy, to close the feedback loop, and what we call matter, so matter itself, influences the background by dynamically editing, biasing the refractive fields. How? This I don't know. But I have some ideas. It all goes back to the very structure and function of matter. We have seen since de Broglie, since wave mechanics, we have seen that matter is made of basically confined cyclical wave-like systems. And then the de Broglie relationship give a one-to-one connection between energy and a certain frequency, momentum and a certain spatial frequency. And of course, we know, so we from the alternative propulsion community, our anti-gravity junkies, we know that there have been some controversial experiments, especially with superconductors, with macroscopic quantum coherent systems. And these research lines from Bartlett, Professor Modanese, Professor Marino, which also had the pleasure of exchanging some ideas. These research lines come from afar, come from different fields, come from superconductivity, come from quantum field theory, come from non-equilibrium thermodynamics, non-equilibrium physics. You can actually trace back this kind of proposal back to the 1960s, if not before. So people were already expecting strange stuff from superconductors since the 60s. But what is key for me, I think, in the sense of engineering, gravito-inertial engineering, what does it mean? To change the gravito-inertial field with technological means at a much higher amplitude than what normal matter does with natural gravity. Of course, we would like to create a 1G field without using a planet. What is interesting here is that theory and experiment, few experiments that have been done with this stuff, suggest that to create strange effects, perturbation of the gravito-inertial field, you need strongly non-equilibrium systems. YDCO, superconductor transitioning to and from the superconducting phase. And I strongly suspect this has to do with the wave properties of matter during the transitional phase. We actually do not have yet. We do not have. So the mainstream theories do not give us that. We will have to build it or to rebuild it. We don't have a picture of matter. We don't have a picture of what matter does. Picture in the sense of three-dimensional representation evolving through time of what matter does when it transitions from coherent state to non-coherent state. We don't have it. The Einstein's field equation, they are empirically verified only for normal matter, huge distribution of matter, planets, stars, galaxies. And the energy momentum tensor of a transitioning superconductor from normal to superconducting phase, I doubt that anybody has really wrote it down and can be absolutely certain of what it looks like. All of this to say what? Einstein's field equation, so the core, the engine of general relativity, is probably just, what do you say, thermodynamic, fluid dynamic limit of something of a much wider theory, of a much wider variety of degrees of freedom. And non-equilibrium systems, strongly non-equilibrium systems, especially quantum macroscopic objects, which act like a kind of amplifier of the hidden cyclic periodic wave-like properties of matter, are, I think, a key to understand how the matter closes the circle and how the matter dynamically influences the refractive background in which matter itself propagates. So to paraphrase the famous quote by Wheeler, is not that matter tells space how to curve and space tells matter how to curve. It's more that, like, matter tells the substratum how to change its refractive index, and the gradient in the refractive index tells matter and light how to bend the trajectory. There must be a mechanism. There must be a mechanism by which matter does it. It's physics. It's no fringe. There must be a mathematical law connecting it with the intrinsic cyclical properties of matter. If gravity is generated by energy, and energy is a measure of the cyclicity of the internal process, and if our equations are valid only in the steady state regime, as they are, it means that there is room for experimentation, for theory. There's really nothing in the accepted physics that forbids this, especially general relativity. And this will connect, I'm sure it will happen, with research lines which come from totally different places. Non-equilibrium thermodynamics, information theory, the fundamental theory of life. What is life exactly, beyond the chemical reaction? That life is bigger than that. And it is connected with, for sure, with the lambda term in the Einstein field equation. Modanese has written a lot about this, but not only Modanese. And so that's it. This is the possibility of gravito-inertial engineering. And this is where I'm at now. So we arrived at the end. It's 1 hour that I'm talking. I think it's enough. What have we done here? So we did a little historical conceptual analysis of the foundational theory of modern physics, quantum mechanics, special relativity, general relativity. And this suggests that gravity can be unified with the rest without inventing strange stuff. The research program proposed by the Broglie has not been brought to conclusion yet. We simply do not have a theory of a propagation of matter in 3D. We just use statistical methods that tell us when a certain detector will fire or not fire statistically. And we have a very refined system of algorithms for predicting the spectra of atomic and molecular systems. But more than that, nobody has ever understood how electrons propagate through slits or photons. There's no consensus on this. So the research is open. It's open season. The analogies between condensed matter systems and plain old wave physics, traditionally studied by optics, and what is thought to be the fundamental physics are too many to be ignored. We are seeing here like a fundamental principle that expresses itself at various levels in the universe. In what we call fundamental matter, in what we call the fishbowl universe, it cannot be a coincidence. So this is more the beginning of a journey. This is like a vision that I give. It is open to editing, to criticism, feedback, and there's work to be done. And it's and if it's done in the right way, in the right order, with the right amount of historical and conceptual examination of already known physics, we can get to a useful technology, a useful gravito-inertial engineering in a relatively short time. This is what I have to say tonight. I'm open to discussion, criticism, insults, whatever. This is a work which I bring forward in my spare time when I'm not doing engineering, when I'm not doing all the other things. And I love this. It's a passion which I had since before starting to study physics. All my collaborators and friends can testify for this. So I'm very thankful for this, for having been given this opportunity. And if you have something to say, to ask, to comment, feedback, I'm here. Thank you.
Tiziano, let me thank you so much. So what I'm going to do is take down the slideshow, and actually let me ask you to send that to me. I'm going to put that up on the actual page.
Okay.
I'm going to bring in Brendan, Isaiah, and Gerald here really quick. Everybody, please give Mr. Tiziano Fulceri a tremendous hand. Thank you. That was a wonderful, wonderful, incredibly detailed presentation. So we do not have time for Q&A on this. We have to jump right into Brendan's. But again, I'm going to put the presentation up, and people can find you online.
It's okay.
Also. Okay. Okay. Well, again, thank you.
You can find me at my website, www.newwavesmechanics.net.
Okay. Newwagemechanics.net. Okay. Yes, and I will put that up as well.
New Wave Mechanics.
Newwavemechanics.net. Okay. Thank you so much, sir. Thank you so much. Okay, so I'm going to, we are 1 minute over, so I'm going to take Tiziano out of the stream. Sir, thank you yet again. It is, again, the work that you guys are doing is absolutely tremendous. We have just top tier, we always have top tier guests, but today I am especially privileged. Brendan, you are definitely one of our top tier guests as well. Sir, it is a tremendous honor to have you with us. You're going to be talking about subquantum kinetics. We talked before the conference. So you got involved with Dr. Paul LaViolette's work in 2018, and you started a group and you collaborated with him for several years until his recent passing. And so just on behalf of the community, thank you for carrying the torch of what he started. And thank you for helping develop this further as well. When you sent me over your presentation, I was just blown away. It is so amazing. So I'm going to put that up now. That's the first slide there for subquantum kinetics. And sir, take it away. And again, thank you. It is truly an honor to have you present this work. And this truly honors the legacy of Dr. LaViolette as well.
Okay, hello everyone. Today I'm going to give a talk on subquantum kinetics, invented and developed by the late Dr. Paul A. LaViolette, 1947 to 2022. My name is Brendan Darrer, and I'm CEO at the Starburst Foundation. And I would also like to thank Dr. Justin Coven for helping me put this presentation together, and also the other members of the Model G Vortical Motion Group. So this lecture was taken and modified from a report, which you can find on ResearchGate at the link below, called An Explanation of Model G in Subquantum Kinetics. And it was put together by myself and Dr. and Paul LaViolette. And it basically is excerpts from the first part of the book, Subquantum Kinetics. Okay, these are two important books for this talk. One is Subquantum Kinetics, a systems approach to physics and cosmology. And the other one, which you may well be familiar with, is Secrets of Anti-Gravity Propulsion. So the Subquantum Kinetics book basically goes into the physics behind the anti-gravity book. The anti-gravity book doesn't go deeply into the physics. Books can be purchased here at etheric.com shop online, and the Secrets of Anti-Gravity Propulsion can be obtained from Amazon. Dr. Paul LaViolette's additional work can be found here at the Sphinx Stargate and at the Starburst Foundation. So subquantum kinetics is the physics model that Paul LaViolette used to model and understand the different anti-gravity propulsion systems discussed in his seminal work, Secrets of Anti-Gravity Propulsion. Okay, limits of physics. When the conventional physics was being defined 100 plus years ago, the computational tools available were limited. Thus, simplifications were made. Those simplifications have confounded physics development for many decades. Subquantum kinetics removes those simplifications in order to enable physics development. Thus, what is being taught here in this presentation is a radical departure from what has been taught in the past and is familiar. Introduction to SQK, or subquantum kinetics. In contrast to the conventional paradigm, subquantum kinetics conceives process, not structure, to be the basis of physical existence. This new approach to physics postulates an active, interactive subquantum substrate whose processes give birth to and continually sustain the physical form that makes up our universe. Subquantum kinetics is a novel microphysics paradigm that incorporates open system concepts previously developed in the fields of general systems theory and non-equilibrium thermodynamics. So we are treating nature and subatomic particles as open systems, which leads to a very different interpretation and mathematical description of the same phenomena that conventional physics deals with. I'm going to give some history of SQK or some background to it. SQK is derived from open reaction systems, which spontaneously evolve well-ordered wave patterns. These open reaction systems were pioneered in 1952 by Alan Turing for his explanation of the symmetry breaking stage of embryonic development. In 1958, Belousov discovered that a solution containing bromide ions, malonic acid, sulfuric acid, and a small amount of Serof's ions will spontaneously oscillate as an open reaction system. In 1970, Zabotinsky and Zayakin reported that a modified version of this reagent would produce slowly moving concentration fronts called chemical waves. These reaction diffusion waves were made visible as changes in color between red and blue when the oxidation reduction indicator ferron was added to the reacting solution. See figure on the next slide. Such patterns are termed Turing patterns, after Alan Turing, who discovered them. So here we see a chemical wave, the Belousov-Zabotinsky reaction, an open reaction system. Chemical waves in the Belousov-Zabotinsky reaction. The reaction has turned red in the darker regions and light blue in the lighter regions. So these are basically chemical waves of an open reaction system, and they're self-generating waves. They don't understand quite how they generate themselves, but they're self-generating, and that's basically what Model G is based on. Turing's work became better known in 1967 when a group at the Brussels University published a series of theoretical papers on spatial instability in homogeneous chemical systems. A reaction kinetic model known as the Brussellator, figure on the next slide, SQK or Model G is a simple extension of this. This two-variable model holds the distinction in the field of reaction kinetics as being an archetypal reaction kinetic oscillator, comparable in simplicity to the simple harmonic oscillator of wave mechanics. And so subquantum kinetics or Model G is taking ideas from chemistry. So it's like chemical waves as opposed to mechanical waves. Here is a schematic of the Brussellator reaction pathways. So we have the inputs A and B and the outputs Z and omega, and X and Y make up the chemical waves, the chemical pattern. The Brussellator is the simplest reaction system known to produce wave patterns that have well-defined wavelength properties, and this is important in developing a soliton particle in Model G. Subquantum kinetics is an adaptation of the Brussellator, adding an extra G component, where X and Y and G are the components or subparticles of the ether. Particles are the standing waves of the reacting and diffusing subparticles of the ether. So the diffusion of X and Y and G components are what make up the electric field and the gravitational field. So X and Y make up electricity, and their displacement produces the magnetic phenomena, and G makes up the gravitational field. Reactive behavior of the ether. As constituents of the ether, etherons play a role which is analogous to that of atoms and molecules in a chemical reaction system, or neutrons and fissionable atoms in a nuclear reactor. As a result of their random motion, etherons have a certain probability of colliding with one another and subsequently of interacting. If the collision involves the right combination of etheron types, a transformation could occur such that at least one of the etherons changes from being one species into being another. See figure on the next slide. Okay, here we have two types of reactive behavior. In A, for subquantum kinetics, in A, a multi-etheron interaction, and in B, a solitary transformation. Etheron species that serve as inputs to a transformation are called reactants, while species yielded as outputs from a transformation are called products. The terms reactants and products are more often used to refer to the ether substrates rather than their etheron constituents, since this reaction kinetic approach usually adopts a macroscopic collective description of these processes. Etherons react with one another along certain preferred pathways. For example, the autocatalytic reaction shown above is illustrated in figure A, two slides above. So this is the autocatalytic reaction. 2x plus y goes to 3x, and k and minus k are the reaction rate constants. And so that's figure 2. That's representing this number A. 2x plus y goes to 3x. Where x and y represent the concentration values of the x and y substrates, and where K3 and K-3 represent the forward and reverse reaction rate constants or kinetic constants for this transformation. Such equations are called state equations because they describe how the constituent elements change from one state or form into another. A set of such equations would be used to specify the ether reactions that produce our physical universe. Okay, diffusive behavior. Besides reactively transforming from one type into another, etherons also move in space. Like molecules in a gas or liquid, etherons exist in a state of random motion, continually colliding with one another. Due to their Brownian motion, they have a tendency to diffuse from regions of high to low concentration. Just as with molecules, at a given point in space, the direction and rate of diffusion of etherons of a given type depends on the direction and steepness of the slope in the prevailing concentration of those etherons. The steeper the gradient, the concentration gradient, the more rapidly etherons will diffuse down the gradient. Ether substrate fields and field potential. There is a one-to-one correspondence between concentration and the concept of field potential used in quantum theory and also conventional physics, such as gravitational potential is joules per Newton, and electric potential voltage is joules per Coulomb. But here we're dealing with concentration. To clarify this correspondence, we define the quantity called the ether substrate potential, phi I, which is the difference between a species' actual concentration and its homogeneous steady-state concentration. E.g., phi x equals x minus xo. So xo represents the vacuum state, the homogeneous steady-state concentration where no particles, there's just ether, there's no particles being formed. See figure on the next slide. So here is a relation of the ether substrate potential for phi x. Remember, phi x is called the potential, but it's a concentration. It's corresponding. Whoopsie, can't see that. corresponding etheron concentration. So here we see in terms of x, we see the x value of concentration, the actual concentration, the XO, which is the homogeneous steady state vacuum state, and phi x. And phi x, which is the etheron potential of x, can be positive or negative, but the concentration is always positive. Model G, toward a unified field theory. Contemporary field theory finds its roots in 18th and 19th century mechanical ether theories. Those theories conceive force fields to be states of stress in an underlying ether substance. While material particles were acknowledged as the sources of fields, there was no theory then available that would explain how particles generated their fields. Particles were assigned attributes such as mass and charge, with no attempt being made to delve further than this. Contributing to this conceptual split between fields on the one hand and the producers of fields, particles, on the other, was the practice of regarding material particles as being physically isolated from the ether. Thus, an inherent dualism became structured into early field theory. Namely, particles were understood as the source of force fields, yet they were at the same time considered to be separate from those fields. Although the ether theory was abandoned at the start of the last century, the force field concept was retained together with the mechanistic framework in which it was couched. Consequently, this field source dualism became transplanted into contemporary physics. This dualistic framework has proven distasteful to theoreticians seeking to construct unitary descriptions of physical phenomena. For example, this fragmentation of physical theory was noted by Einstein, who wrote, so this is Einstein writing, "In Newtonian physics, the elementary theoretical concept on which the theoretical description of material bodies is based is the material point or particle. Thus, matter is considered a priori to be discontinuous. But when in the second half of the 19th century the laws of electrodynamics became known, it turned out that these laws could not be satisfactorily incorporated into the Newtonian system. The introduction of the field as an elementary concept gave rise to an inconsistency of the theory of electrodynamics as a whole. Maxwell's theory, although adequately describing the behavior of electrically charged particles in their interaction with one another, does not explain the behavior of electrical densities, i.e., it does not provide a theory of the particles themselves. They must therefore be treated as mass points on the basis of the old theory, Newtonian physics. The combination of the idea of a continuous field with that of material points discontinuous in space appears inconsistent. Einstein believed that the physical reality of space would best be represented by a continuous field, and that all physical phenomena, including particles, could be described by the appropriate solutions to the equations representing this field. As shown here, it may be possible to realize the long-sought goal of unitary field theory by working within the fertile framework of subquantum kinetics as Model G. Model G is a non-equilibrium, non-linear ether reaction scheme. So Model G is basically a non-linear reaction diffusion system with non-equilibrium thermodynamics. So on one hand, it starts off above average complexity for science, but it's also, when you look at the different physics scenarios, it can also be looked at in a simple way. So it's both more complex and more simple. Model G is a non-equilibrium, non-linear ether reaction scheme that is specified by the following 5 kinetic equations, which represent ether reactions that take place among various etheron constituents. Reaction scheme of model G. So here we see the chemical equations of the reaction scheme of model G. So A goes to G, G goes to X, B plus X goes to Y plus Z, and 2X plus Y goes to 3X, and X goes to omega. And there's also reverse reactions, but most of the reverse reactions we can neglect. They're negligible. The only important one is this one here. This G goes to X, and then the reverse, which is much smaller, of X goes to G. And I'll talk about that in a bit. So here's the reaction scheme of model G, similar to the bruslator, but just one G component added. So A and B come from A prime, A double prime, B prime, and B double prime. You don't really need to know about the primes and the double primes. Just they come almost out of nowhere. They could come from a higher dimension, or they could come from the three-dimensional universe as we see it. And they exit through Z and omega. And then X, Y, and G make up the physical observable universe. And so X and Y represent the electric field, whose spatial displacement produces the magnetic component, and G represents the gravitational field. And G G may be part of magnetism as well. We don't know yet. So here is a hydrodynamic analogy of some of model G's reactions. So here we have containers of water flowing in at the top, flowing through each container and through G, X, and omega, and the area of the orifice of the water flowing out of the container, that would represent the reaction rate constants, the kinetic constants K. And we've also put in this reverse reaction, which is very important, of X goes to G. So the forward reaction, which is larger, is G goes to X. Then the reverse reaction is X goes to G. And this makes G dependent on X, and that's basically your electrogravitic connection right there, that reverse reaction. And also this reverse reaction is important for producing, for G being the bifurcation parameter. I'm not going to go into bifurcation parameters at the moment, just to know the bifurcation parameter of G and X going to G is the electrogravitic connection, and also it enables the soliton particle that we'll look at in a moment to become stabilized. A suggested expansion of the model G ether reaction scheme as it would appear disposed along the T dimension. Now this dimension could be within the three-dimensional universe, or it could represent higher dimensions. G, X, and Y mark the domain of the physical universe. Here we see the reaction diffusion equations of model G. 3 equations, the first one describing the rate of change of the G concentration, then the X concentration, and then the Y concentration, the rate of change of concentration. And the first term in each of those equations, the D divergent squared G, that represents the diffusion, and all the other terms, the K terms, represent the reactions. And we also see in the second equation at the end this chi term. At the bottom, you can see the chi term there. That's the seeding the reaction. That's the 0-point energy fluctuation that seeds the soliton particle and allows it to grow and develop. Otherwise, we'd be waiting millions of years for it to happen. Two important features give model G and the bruslator their ability to spontaneously evolve ordered concentration patterns. These are autocatalysis, or positive feedback, which gives the system its nonlinear characteristic, and cross-catalysis, which gives the system its tendency to oscillate. Model G has, so autocatalysis, I'll just describe it here a little bit. Autocatalysis is, chemists call this double input sharing between positive feedback or autocatalysis and coupling. Coupling is evident in the linking of the two distinct reaction pathways. A goes to X goes to omega, and B plus X goes to Y plus Z. Chemists call this double input sharing cross-catalysis, since reaction products must cross over from one reaction to another to form a closed-loop catalytic reaction promoting effects. So it's probably a bit too much to go into all of that in this presentation. Model G has only one autocatalytic reaction, i.e. positive feedback. Step 3.1d in the following slide. So here we see 3.1d, 2x plus y goes to 3x. As more x is produced as a product on the right-hand side of this equation, so that's the 3.1d. As more x is produced as a product on the right-hand side of this equation, more x becomes available as a reactant on the left side to convert y into x. Hence, x has the tendency to grow exponentially with time. This growth does not proceed unchecked. It is brought back into balance by the reaction step 3.1c, which converts x back into y, thereby forming step 3.1d. There's 3.1d there. I just told you about 2x plus y goes to 3x, and 3.1c there. B plus x goes to y plus z. The system's ability to generate periodic structures emerges as the result of the interplay between these growth and balance processes. Okay, so here's the soliton particle. This is the simulation results when these equations are solved in one dimension with 3D symmetry. And on YouTube, you can see it on YouTube, but this, if you look under that, spontaneous nucleation of a nascent neutron from 0-point fluctuation. So the first slide is the empty state, the vacuum state. It's not really a vacuum, but let's call it a vacuum. It's a homogeneous steady state where there are etherons, but there are no particles being formed. Then it is seeded by a chi function, 0-point energy fluctuation, and that enables the particle to form. So you see the first, and then the last slide, you see a fully formed soliton particle with phi g. So we're just calling them G, X, and Y, but they're potentials. They're phi G, phi X, and phi Y. So as G goes, G is dependent, is coupled with the X, the electric charge potential, and as X goes negative, G also goes negative. That's the electrogravitic connection, and also enables the particle to become stabilized, and also to be able to produce localized structures as dissipative solitons. Because in the busylator, it just produced a series of waves. It didn't produce a localized soliton structure. So let me just see if I can show you that in a bit more detail. Tim, can I share my screen?
Yeah, in fact, so why don't I do this? You can. So if you go to present, what I'm going to do, you know what? Actually, let me do this. There we go. Perfect.
Okay. So that's that. So let me just
and change tabs. Yeah.
What do I do then? Just go to
oh no. In your browser, actually, you're gonna have to switch windows. You probably won't be able to see yourself while you do it.
I won't be able to see myself, but it's still not okay. So can you see it, Tim?
Yeah. Looks perfect.
Okay,
sir.
so here's a model G soliton particle as a neutral subatomic particle, such as the neutron, and we can see that on the y-axis we have potentials as concentration, and on the x-axis we have one-dimensional space. So you can see the smaller wave is the G potential, and that's dependent on x, and the fact that it goes negative with x, that's the electric. So when x is negative, G is going to be negative. An antiparticle, it'll be the opposite way around. They'll both be positive. Okay, let's just go back to Okay, I'll go back to my presentation now. Concluding remarks. SQK conceives the electric field potential, so that's like voltage, but joules per coulomb. But in model G, we're talking about it in terms of concentration, number of particles per unit volume, and their reaction and their diffusion. So SQK or subquantum kinetics conceives electric field potential, ether concentration gradient, and magnetic field, ether vortex currents, as being seated in the ether, as opposed to being attached to field sources that generate them, such as in the conventional physics. Since 2018, the Model G vortical motion group has been attempting to progress subquantum kinetics by including vortical motion or rotation into the reaction diffusion equations in the hope of modeling quantum particle spin. At present, physics has no official conceptual model of what spin is. It just assumes it as a property of subatomic particles. SQK attempts to go further and explain the details of how spin forms. Utilizing the open system paradigm, subquantum kinetics, or Model G, allows us to analyze many propulsion and over-unity energy technologies that cannot be explained by conventional physics. The electrogravitic technologies which thus far have been explained using the SQK paradigm are in the following slides, coming a bit later. Subquantum kinetics also provides a useful paradigm for understanding how unbalanced electrostatic or magnetic field forces can induce a net propulsive thrust, as in the case of T. Townsend Brown's asymmetric capacitor and the NASICA superconducting thruster. From what I understand about NASICA's thruster, because I've been reading the SQK book, is that it didn't work out the way that they hoped it would, because I'll explain when I get to the slide. So, okay, the first one is one of Brown's. I'm not going to go into details of this because I don't know it very well. I just know that Paul had said that these technologies can be explained by subquantum kinetics. So this one here is Brown's circular flying disk, and the positive charge at high voltage is producing a lot of positive charge at the front of the disk, is creating a gravity well, so it's pulling the object, and at the back the high voltage negative charges are producing a gravity hill, so they're pushing the object. So it's got this pulling of it and it's pushing it, and that's both in the Subquantum Kinetics book and The Secrets of Anti-Gravity Propulsion. Here is T. Townsend Brown's asymmetric capacitor. I'm not going to go into details of it. You can find that in the SQK book. Townsend Brown's electrogravitic thruster, also in the SQK book. And NASICA's superconducting thruster. And for what someone said, the first version, one of the guys in our group said the first version worked, but I'm not sure if that's true, because I think Paul had mentioned it in his book. But he mentions that according to the conventional theory, it should work. So I think it's supposed to be disobeying Newton's third law. For every action, there's an equal and opposite reaction. But Paul says in the book that disappointingly it didn't work, but subquantum kinetics can explain why it doesn't work, because it's making use of ampere forces as opposed to Lorentz forces. So that Paul explains in the book why it didn't work. Well, it's a bit disappointing that it didn't work, he said, but he could explain it through subquantum kinetics. And here is the Bogdanov gravity impulse beam generator. Could knock objects over several kilometers away, maybe even 200 kilometers away, and pass through several inches of steel. And it's basically using the Geon field to knock over objects at large distances away. I don't know a lot about it, so I'm not going to go into it in detail. And also the Searl disk. So these are all things that Paul Laviolette said could be explained by Model G. So I could do this in a future lecture, but I'd have to research up on it more. Okay, thank you for your time. I can't hear you. You might be muted.
Oh, I am. My apologies for that. Let me take the slide out. Wonderful. Brendan, thank you so much. So what I'm going to do is I want to bring everybody back in here. And they don't know I'm bringing them in, so they may not even have their cameras on. But you know what, Brendan, let's give you an enormous applause for a wonderful presentation. Thank you so much. And, you know, we have lots of time, too. And since we have the guys up, if anybody wants to ask questions that I just brought in, you know, Isaiah or Curtis, looks like Gerald may or may not be here. Looks like his speaker, his camera is kind of slow. And let me go in here. You know, we can also, again, we can throw up stuff from the comments on the field here, which is pretty exciting. Oops. I'll put some of those up. Let me see. So Mike Doss is asking about flybacks. Mike is our flyback guy. You know what? Let me go to Paul's. Here we go. Has anyone seen Searl disk replications with 3 tiers of rings and rollers? I'm not sure. That's not really La Violette stuff, though, is it?
He was saying that subquantum. I think he analyzed the Searl generator and could explain it through subquantum kinetics. But I haven't analyzed it myself, so I can't. I'd have to research up that. I'd have to research that up and.
Well, and I know Isaiah is going to be doing like a knockdown drag out on the Searl effect later today, which is again super exciting. So, in fact, Gerald turned me on to that. He said Isaiah is like doing higher quality. He's actually following the directions, doing the perfect job that like everybody else should have done, but no one has ever done before on Searl. So, let me see. I saw one on Townsend Brown. Yeah, this person's saying Townsend Brown, one of many who went down the rabbit hole. Townsend Brown definitely did that. He got really in depth. I think Paul's work is probably closest to T.T. Brown's too, right?
Yeah, it's quite close to it.
Yeah.
He referred to Townsend Brown quite a lot.
So in terms of the analysis that you've done, what would you say probably the best approach would be for building a device?
For building a Townsend Brown disk.
Yeah, I mean, because again, I'm going back a little bit, but everything that I recall from Paul's work, he got so deep into the not electrostatic, but electrokinetic forces, right? And to me, that was always T.T. Brown related. Was there a particular one that might be the best, or?
In order to try and start from scratch and try and build one.
Yeah.
I would have thought that the first diagram I showed there of the disk, if we weren't able to get Brown's patterns, because you have to build up. I mean, you don't necessarily have a lot of power. You can have quite small micro currents, but very high voltages, like 50 kilovolts. But the power doesn't have to be very. If the current is very small, the voltage can be very high, and the power is just moderate, or it could be a little bit high. But so you need to produce high voltages to go through his patterns or the information available. And I think the SQK book is a good starting point. The anti-gravity book is very good. I haven't read it. I've only read the first few chapters of the anti-gravity book, but the Subquantum Kinetics book goes into more of the physics behind it, and that looks like quite a simple device. But the first diagram I showed there,
kind of the T.T. Brown,
it requires high value dielectrics. That's something I do know.
That looked kind of the T.T. Brown rotator a little bit.
Sorry?
The disc almost looked like the T.T. Brown rotator, right? Where you had 2 discs and they were suspended and they rotated around.
Yep.
Yeah.
Okay. I mean, one of my colleagues, Justin Coven, Dr. Justin Coven, he's given a talk a few months ago on APEC. he was kind of questioning how much electrogravitic, he thought that if electrogravitic, it's just his thinking at the moment, but he thought if electrogravitics had been solved, we might see more of these objects. But I tend to be a bit more conspiratorial than him. He thinks that people might be able to build them more simply, and that it'd be difficult for people not to show video of these antigravitic effects. But I think that the people in black projects or wherever who if they've got these devices working, I think they would take down YouTube videos of electrogravitics.
Well, as I remember, yeah, I remember a lot of people ascribing the B2 bomber, right? They were looking at subquantum kinetics from the B2 bomber perspective, and there was that thing about, there was some news story about the B2 using some kind of electrogravitic drive, and it was kind of like a rumor that was going around. And then people had come back to subquantum kinetics and said, look, this could explain how the B2 might work. And in some ways, they were talking about the leading edge of the wing being charged relative to the body. And that reminded me actually a lot of the image that you showed. So,
yeah, on the very simple level of subquantum kinetics, when you're building up positive charge, a lot of positive charge on one side, that's creating a well. That's great. So it's pulling the object. The negative charge, which has come about on the rear, that's creating a hill. And you even have this within the atom of a hydrogen. You've got the electron and the proton of the nucleus. Now, Paul explains how this works within the SQK book, so you've got a lot of negative in T. Townsend Brown's flying disc. You've got a lot of negative charge on the rear, and that's creating a hill, and it's pushing it. So that's in a sense, it's very simple to analyze it like that, So, and I know that T. Townsend Brown was using high value dielectrics to get the voltage up to high voltage, but with small current.
Yeah. Well, does anybody else have any questions who was on it? We're a little bit ahead of schedule, which is that's not a giant. Jared, oh wait, and Jared's hiding in the back. Jared, I thought I brought you in. You must have taken yourself out. Mr. Yates, what are your questions, sir?
I was having internet issues. Brendan, excellent presentation. I'd really like to know, out of the different experiments that you mentioned, and maybe some that you didn't mention, can you think of one experiment that would have the greatest likelihood of demonstrating LaViollette's theory?
Let me just well, I think that you probably go to over unity free energy over unity technologies, such as the HHO water-filled cell. But yes, that I mean, I've seen a video of someone using a kind of aluminium foil device and charging it up, and it was levitating. I mean, things like that. I think so. If you, to tell you the truth, I don't really know which one is the best one to do. But if you read his book, especially Subquantum Kinetics, he's gone into his 5th edition is 570 pages. So he's added, from the 3rd edition, he's added about 200 pages. And but to tell you the truth, I've really been focusing on the particle physics side, and I haven't really gone into the electrogravitics a lot. So maybe I'll have to research it up and give a talk another time on that. And then I'll be able to tell you which one.
Awesome. Anybody else have questions? Again, we're about 15 minutes ahead, but if not,
if I may, one question.
Yeah, go for it, Tiziano.
Yeah. Did you already use this model that you presented to analyze the one or two or more experiments, and to we've done some... Okay.
You're muted.
Sorry, I got an interruption.
We've produced soliton particles accelerating and bumping into each other and moving apart. And that's in one of the papers on my ResearchGate site. Let me just go to it here. So that's the one that we've done experiments on. Is let's give you the name of the paper. It's just a report. It was just uploaded to ResearchGate. So subquantum kinetics, simulating subatomic particles.
I can find you on ResearchGate.
Sorry?
Oh, yeah. I think he's looking for the...
I can find you on ResearchGate.
You can't find it. Brendan, just put Brendan Darrer ResearchGate. So we used a G gradient to accelerate particles down a G gradient, and in 2 dimensions. What was your question again, Tiziano?
The question was, did you already use this model to analyze some strange experiment which could not be explained with normal stuff?
Yeah, Paul has basically done that. I mean, he's studying this since 1973. He developed subquantum kinetics between 1973 and 1984, and he's done loads. He's mostly in astronomy, but he's also done alternative over unity free energy, anti-gravity. He says there are some devices that he can't explain, but a lot of them he can explain. So basically, he's breaking the laws of thermodynamics. The first law, non-conservation of the first law, breaking the second law, which is that the heat flows from a hot region to a cold region, and you can't get more out than you put in. These solitary particles are generating themselves. It's easy to break the. Yeah, but you could think of these.
It's easy to break the laws of thermodynamics. It's just that when you use an open system.
Yeah. I mean, all these
already broken
devices, anti-gravity,
the first
are breaking. You can break them in. You can perform experiments in your backyard that break the laws of thermodynamics. Because go on.
A lot of people cite the laws of thermodynamics, but they always forget the initial assumption, which is like within a closed system, within a closed and isolated system, blah 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 blah. But if you just remove that causal at the beginning, then you've already broken them. So you're not within the scope of the laws. So it's very interesting.
Okay, thank you.
Yeah. Well, yeah. So again, and let me see. Yeah. So there's Jared's. And there's Jeremiah. Let me get Jeremiah in here. Jeremiah.
Yes, sir.
Yeah. Can you turn your camera on, sir?
I cannot. I'm actually not even. I'll be honest. I'm not even sure yet. I just made it in time to ask and forward a question from Gabriel, who's another one of our co-researchers.
Yeah. Can you ask that? That was why I brought you in, because I know that you're really excited about this stuff.
So Gabriel was super interested in LaViolette's work, and he's got the books, and he was referencing something that I hadn't read about because I don't have his book. And he was mentioning that LaViolette talked about a capacitor that apparently had some kind of recess where you could place an object into it. And apparently when stimulated, this capacitor would cause the object inserted into it to vanish or appear to vanish at least. And he was asking if you could speak to that or maybe give any information on that. I don't know. I don't know exactly what he's talking about, but if you do, I would sure love to hear it. And Gabriel,
I think that's in the SQK book, 5th edition. He does talk about capacitors and pendulums. Let me just quickly look up there a minute. So I need to get the SQK. I think that's in the electrogravitics. He's got a section in the book on electrogravitics. Not sure if I'm going to find this. No.
Yeah, I'd love to see that reference too, because it sounds like an incredibly fascinating phenomena. We've seen, like in Hutchinson's videos, objects appear to vanish as they're,
Yeah, Paul knew John Hutchinson and worked with him. I don't know how many times. I think he's at least met him on a number of occasions, several occasions. I don't know how many. So, let me just see if I can find it. Anyway, it's in the Subquantum Kinetics book, and it's under. I think it's a pendulum and a capacitor, and that's one of the simpler ones to do. I think it's a pendulum and a capacitor. I think there's liquid helium or something like that, but you have to look it up. I just can't find it just straight away.
Well, thank you very much for at least addressing the question. I guess maybe we can perhaps talk at another time and maybe get into it. I'd love to get Gabriel on there as well. He's done a tremendous amount of investigation, and he's a quite young lad, you know, just getting into this and finally starting his own experiments. So he's really primed to start and play with this stuff, and all this input information is going to help him along his path like it's helped us all.
Okay, thank you.
Thank you.
Yeah, well, and Jeremiah, thank you as well. Yeah, again, Paul Laviolette's work is foundational work, right? Yeah, I mean, he went back, like T.T. Brown is foundational, and Paul really went through and analyzed that and turned it into subquantum kinetics, right? That's where a lot of the inspiration came from. So, you know, I think it's so valuable for people to study this. And again, Brendan, I can't thank you enough for, you know, carrying the torch on this, because you know, otherwise, this is something that could potentially be lost, and that would be a real tragedy. I mean, it would be incredible tragedy. So,
thank you very much, Tim. Thanks.
Absolutely.
Tim?
Yeah, Jared, go for it, sir.
I just wanted to know if we do have an extra minute or two, if I could ask Tiziano a question from his presentation, since we didn't have time at the end.
Yeah, I would say go for it.
Same question to you, Tiziano, that I asked Brendan. Can you think of any experiments that would help to validate your idea?
The experiment is always the same. Experiment is to reproduce what Poteknov did, because nobody ever reproduced that experiment properly. Do the transition, do the fast transition between superconducting and non-superconducting, coherent quantum system and non-coherent quantum system. This has been talked about also here in APEC. I followed previous talks. Maybe it's not about the superconductivity, as Jack Sarfatti said, and I think he's right. But we have to understand the principle before, and we have to get hold of that one experiment that we know that produces the effect. Because I spoke with Professor Giovanni Modanese, I spoke with Professor Giovanni Marino. We tried to do the replication at the Polytechnic of Turin in Italy. He knew all the relevant researchers. He has a background in general relativity and experimental superconductivity. He said nobody ever properly reproduced the 1992 and 1996 Poteknov experiment. And Giovanni Modanese, Professor Giovanni Modanese, is a pure theorist, so he never touched anything. Now, that's the experiment.
Wasn't there a very difficult part of Poteknov's experiment, though, where the disk was so large that to spin it at the speeds necessary, it just flies apart?
That's not that's step one. It's the step 0 which is hard, because he claimed to have done a monocrystalline B-layer disk. So there are two slightly different materials, doped with slightly different doped, and they are monocrystalline, which is, I don't know, alchemy. I don't think there are many people on this planet now able to produce something like that. But on the other hand, investigation by Professor Marino, both theoretical and empirical, experimental, suggests that actually, if you want to have the strange effects, you have to have a bad superconducting sample. So you have to have a superconductive and non-superconductive region, because it's not only the time transition between normal and non-normal state, it's also the space transition. So if you have a sharp transition between a normal part of the material and a superconducting part of the material, then you can have flux spinning, and apparently this is what does the magic, apparently. But I never did the experiment. I would really like to do it. It's expensive. It's not only expensive, you have to have skilled people. And you know, you don't learn to make superconductors by chance. You have to be trained for years in specific labs by specific masters. So that's difficult, but that's also the good thing, because if it's difficult, it means that there's not so much competition, and there is also some kind of justification of why it has not been done yet after Polkadnov. This would be my answer.
Wonderful. Well, thank you, Tiziano. And so we're about 4 minutes from the top of the hour. Does anyone else have questions, I guess, for Tiziano or for Brendan Darrer on subquantum kinetics? Okay, well, I think, guys, we're probably just about there then. So let me do this. Again, let's give Brendan another tremendous applause. Brendan, thank you so much.
Thank you very much.
So much.
Cheers, thanks.
Yeah,
Thank you
truly
very
an
much.
honor. And we'd love to have yourself or Tiziano have both you guys back to present in the future on on these or related topics. So what I'm going to do now, Curtis is already with us. Curtis, are you okay starting 2 or 3 minutes early? Okay, good deal. So what I'll do, I'll just bring everybody else back out into the studio and we will get Curtis rolling. Curtis has his presentation here. So I am going to clear out the studio here. Okay. And again, a big thank you to everybody. Yeah, today is so tremendous. I am so excited. Curtis, let me add in your paper. Thank you for uploading this. Again, as I've been proselytizing, one of the bugs with StreamYard, at least as far as I can tell, is that you have to upload the file yourself to be able to go back and forward in slides, which, but other than that, I love this platform. I mean, Mark Sokol got me into it, and Bernie, I think, got him into it. So it's got so many nice features.
Yeah, I don't mind.
Yeah. Well, Curtis,
I think only one of the slides didn't take, but that's okay. It was a minor thing.
Oh, okay. Well, so you're talking about quaternion, spinor relativity, and unification. And then I think this is also how this comes back to Mach effects, right? Because people don't know this, but I was asking James Woodward, I said, Jim, do you want to do a presentation? Come on, do one for us. And he said, I have the guy for you. And then he recommended you. So that is how you ended up at our conference. And I am, again, very appreciative and truly honored, sir.
Well, thank you. Yeah, so I'll say that up front that the Mach effect is a potential result of this theory. And in addition, I mean, there's other things that are potential consequences of it because it's based on relativity, right? So Jim had derived quite a while back using general relativity and other kind of like assumptions about things. His proposal for a Mach effect that he could experimentally test. So I have been in the lab, hands-on, helping him out, and I'll be giving an update at the end of the presentation of the lab work as well.
Oh, awesome. Yeah, and again, I'm just overjoyed. I mean, all three of you guys are just top tier, right? So again, the folks don't necessarily know this, but like every month to 2 months, I'm out there, like who wants to present, who has a great idea, who's working on stuff, and the problem is we do these conferences more than people are able to create stuff, but every now and then, lightning strikes, and this is one of those events. So
yeah. And actually, as I go through this near the end, we might discuss like follow-ons because I'm not able to cover the full thing. I mean, there's so much work that Sachs did. and there's so many things that result in, and it's a different way of looking at things that what we're traditionally trained for in physics. So you want me to go ahead and get started?
Yeah, let me take myself out, and again, I will be here in the background, and everybody's still here in the studio, as you can see. And thank you again, sir. Again, Quaternion, Spinor relativity, and unification, and later applications to Mach effects. So, yeah. Again, thank you, sir. And I will be here watching with glee.
All right. Okay, so let me get started here. So, introduction. Basically, I just wanted to talk about my motivation, how I got interested in the Mach effect. And my interest was because of what I learned about this theory while I was an undergrad. So I actually, for a while there, I was considering working with Jim as a grad student. Life led me other ways, but eventually, over time, I got an opportunity where I could full-time and spend time in the lab and actually help out. So that's been something I've been doing the last couple of years, and that's one of the main things that I'm working on right now. So this presentation, I wanted to put this up front that basically take this as something that kind of maybe set aside, do some lateral thinking, set aside the stuff that we were taught. We're going to start with some basic axioms, basic principles that we know. This is kind of like the methodology that we're going to be going through here. And the other thing I want to mention is I'm not claiming anything. Okay, so basically, at the end of this is a theory. It needs to be tested. I'm not saying it's right. I'm not saying it's wrong here, but it has, from my opinion, it has a chance. And we'll go into why. It's not popular or currently not popular. There's a lot of reasons. People do physics. Physics isn't some entity in itself that just optimizes for the best theory. That's not how things work in the real world. So, so I'm working on finding a prediction that differentiates this theory from other things, right? How can we know that this theory is the way to go, right? So, and the Mach effect is potentially one of those experiments, right? Because the Mach effect will show that, okay, Mach has something going on there, and the issues that, the dismissal, and we'll talk about that. We need to rethink that. So, so just a short history. My interest in physics, I was always, from a young age, interested in physics. I read a Brief History of Time in like a week. I got super interested in it. And earlier there was discussion of T. Townsend Brown. I remember going to bookstores and seeing these anti-gravity books and reading them. I basically read voraciously when I was young, and I was looking for anything and everything because I wanted to understand. In high school, that's kind of what I did. As I took physics and math, and but I was a musician. Okay, so I played basically jazz trombone, and I actually started in college as a music major, and I realized that it was just too much work. I was practicing 6-7 hours a day just to keep up. It's really difficult instrument. And you need to be perfect. So I found that I was good at physics. So I changed to become a physics major. And as a music major, I was at a community college. I started at a community college, and I stayed there and did my physics there. In my undergrad, in my community college days, I actually did all the math courses, and in addition, I did summer courses at Cal State Long Beach, where I learned complex variables and partial differential equations before my junior year. So the junior year is usually when physicists take quantum, and usually in the junior year, most physicists haven't had those math courses, so you kind of learn that in quantum. So quantum was kind of I took to it really easily. I understood what we were doing mathematically. It all made sense. But But I did the same thing. I had the same habits. I would read voraciously at the library, and I came at the time I was a upper division a physics student at RPI. I came across Sachs's books, and I would read anything and everything. There was the standard stuff. It didn't matter to me if it was like not mainstream or not. I read it, and when I came across Sachs's work, I would ask people, in the department, any professor, like, what's going on with this? This seems to like tie everything together, and no one would take it seriously. They just it was just too much. And unfortunately, at the time, even though there was a chance, like Mendel Sachs was, of course, still around back then. He was at SUNY Buffalo, and I could not take the weather. I wanted to become his grad student, but I just couldn't do it. So I kept working on his theory as the theory that I found to be correct, and the methodology in physics that I thought made sense, which was the same that Einstein took. And I came up with several realizations, and we'll, at the end here, we'll talk about a couple of those that apply to propulsion. So, as I mentioned before, I was taught how to do physics, and some of it, a lot of it is self-taught. Actually, one of my professors used to say, Curtis, I can't teach, I can't learn you physics. He was a Texan. So he would tell me that, right? So basically, I was someone that like really did a lot of training, self-training in lateral thinking. Gauss's law is a great example of that. And there's a book called Thinking Physics out there. It's, I think, no longer in publication, but it was like one of my favorite physics books. It didn't have equations, but like thought experiments that you would do, come up with an answer, and then thered be, you would have to come up with an answer first and then see what the explanation is. And that's how I kind of taught myself how to do physics. So here, I'll talk a little bit about the different paths. There was a presentation last time where the presenter went over some different, kind of like high level, high abstraction, category theory type connections in physics. And that's like string theory is another example, right? You're abstracting kind of like a mathematical abstraction, and you come up with something that may or may not have predictive power, right? So one of the big complaints about string theory currently is, it's not falsifiable, right? So you got to be careful with the when you do abstractions. Sometimes they're useful, sometimes they're not. That's kind of the trick, right? There's this subtlety where if you have, okay, this is the principle I'm going to apply. How do you apply it? It's not straightforward, right? Like we'll talk about covariance. That's something that Einstein had to talk to a mathematician, like, how do I do this, right? Whereas now a lot of us are taught with quantum, right, a positivistic, a very empirical way of looking at the world. Because when you do that, I mean, you can get results, you can get answers, but it doesn't necessarily tell you why. Okay, so this is the slide that kind of goofed up. So I'll do a little mathematical warm up and a kind of a historical example of what we're going to apply here to the Einstein equation and Einstein methodology for what he did. So the first part here, I had a little example of a vector of first order. Basically, the vector is a first order tensor, okay? And you can actually factorize that into two quaternions, a quaternion and its dual, or you can think of it its conjugate, right? Like in analogy to complex numbers. So there's a very good course, I would call it, on Spinors that's on YouTube, and it's by Eigenkris. It's one of my favorite YouTube channels. I would highly recommend looking that up and going through that if you want to understand Spinors better and understand how that mathematics is currently used in quantum field theory and quantum mechanics. So the next thing here I have showing is the Klein-Gordon equation, which is that first equation here. You notice that the things are squared, right? You have a second order differential, and you have m squared. Okay, and Dirac, one of the progress that Dirac made is he actually found a way to factorize that, and the way he factorized that is that he can made a Spinor formulation of the theory. Okay, so that is a very similar, I would call it a recipe that Sachs came up with, and so Sachs is kind of the major axioms, I would say, that it's kind of sprinkled throughout the structure of the theory is first of all the principle of general covariance, which is what Einstein implied, which is okay. You have space time, okay, as represented here with the 0, 1, 2, 3, and basically if you're with covariance, if you're doing a transformation of coordinates in space time with any other coordinate system, you will, the laws of physics need to, you guys all should know what covariance is, hopefully, but the laws of physics need to match up, right? The prediction is going to be what happens. That's the way I like to put it. The other axioms that kind of guide the way this theory is used and how it develops is the generalized Mach principle. I'll get into that later as well. The correspondence principle, and of course Noether's theorem, which leads to conservation laws and requirements on the field theory. So, getting right to the heart of the matter. So, this is the way Sachs. I'm not going to go through all the calculations and all the things you need to put in here. There's too much, but the heart of the matter is this. So you have Einstein's field equation. If you notice, the Einstein's field equation is kind of similar in terms of its structure to the Klein-Gordon, in that you have the G and you have two indices, right? And what Sachs did is he took that and he said, okay, well, I'm going to factorize that tensor to quaternions. So you get a quaternion and it's dual. And those duals can combine into, and you can recover your tensor formulation. And when you apply that line of reasoning and go through, you can derive what I call, it's been called in other papers the Sachs field equations, but I just like to call it the Einstein-Sachs field equations, because Sachs did this same procedure with other equations, and we'll go through that here. I'll show you that. But basically, you have a Spinor formulation of general relativity. And the thing about the difference here, the biggest difference, is that with the Einstein's field equations, if you fully use them, you notice that you end up with basically 10 separate equations, right? That are independent. Okay, you can get other equations, but they're basically the same. They have symmetries that can cancel out. So basically, the Einstein-Sachs field equations, you notice that there's the quaternion with one indice. So it's no longer reducible at that point. Just like what Dirac did, you get an irreducible formulation of the theory. So with the Einstein-Sachs field equation, you actually end up with 16 independent equations. And when you combine those, right, you can take conjugates and you can add and subtract them, just like we do. Like, let's say you have complex variable equation, you can take its conjugate and you can add and subtract it, add its conjugate or subtract its conjugate, and you get a real number. You can do the same kind of thing with Sachs's field equations. And if you do this, if you take the addition and the subtraction, you get two different things. When you take the addition, right, that conjugated equation, and you add them, you recover basically a tensor equation that one-to-one matches up with the Einstein field equation. And if you take the subtracted version, right, if you take the minus there, and you work through all the math and apply everything, you end up with an equation where you get 6 unique equations that can be mapped to one-to-one to the Maxwell's field equations. So this is, I call it an apparent unification of gravity and electromagnetism. The question becomes, how are these tied in? What are these quaternions doing? And does that mean like mass and charge and, all these things are tied together? It takes a lot. It took me years and years to think about this and kind of understand it, come to grips with it. One thing to note back there in the mathematical slide that was left out is, quaternion is, you can think of it as a kind of a generalized spinor. So one of the things that was a problem before was that you have relativity not being compatible with quantum, and this is something. This result is something that kind of helps us kind of patch that up. So consequences of I have a slide here that just talks about some of the major consequences of that quaternion formulation. So basically, you get that compatibility of spinors, and also you get a spin curvature. Okay, so there's more there than the standard formulation of relativity and the standard formulation of electromagnetism. So there's other predictions that come out of this. So it's an apparent unification, and applying this. The way I would put it is applying this recipe here, and the fact that space-time can be described this way leads to unification with inertial mass. So first, I want to talk about, or the next thing I want to talk about is the generalized Mach principle. This is one of the axioms that we talked about before. So we just covered, the consequences of covariance fully, applying it fully and correctly, right? So it's not reducible. So you get a set of quaternion or spinor equations that fully describe, what relativity should be. I will mention that you can get solutions like the Schwarzschild solution from this spinor formulation. So it really does match up and give the same and more predictions than what Einstein's field equations did. Kind of an analogy to, like, you get the Klein-Gordon, you get the Dirac, you can predict what Klein-Gordon had, but with the Dirac equation, you get a little extra. For the generalized Mach principle, so first I want to discuss why the Mach principle was rejected. So there was a physicist, Karl Brons. So he basically came up with this argument that it's called spectator matter, and he applied the equivalence principle and said that basically that if mass were if the Mach principle was correct and mass was caused by its interaction, then we would be observing different things for charge, the charge to mass ratio, right? That's something that is observed throughout the universe. And so his argument was that it does not make sense that that just mass comes from that interaction. So instead of ruling out the Mach principle, what Sachs did, and I don't know if he was aware of Karl Brons's argument, probably was, but he generalized it. So basically, he applies the Mach principle to mass, charge, and magnetic moment. Basically, all the manifestations of matter come from the interaction. Okay, so that's how that's taken out. So now the next principle I mentioned earlier is the correspondence principle. So we got to ask yourself, like, okay, so if you have a unification, okay, we have quantum mechanics, we have all those observations. If there's a theory that is describing everything, including matter, how can quantum come from it if general relativity only had real numbers, right? With Einstein's formulation, you only had real number variables in that equation. So this formulation of general relativity uses quaternions and uses spinors, and you can reduce it to complex numbers and real number systems. So that issue goes away. And so with that issue gone, you can now say that, okay, well, using the correspondence principle, if quantum mechanics is supposed to come out from this formulation in the linear limit, right? So you take a linear limit of the formulation, then you need to have a first order homogeneous differential equation that describes inertia, right? Because remember, quantum mechanics fundamentally came from the observation that matter are waves, okay? So here's how Sachs went about figuring that out, right? So he used that principle and said, okay, well, we have, the Dirac equations. I'm going to set M, which is the inserted mass, right? So that's like in quantum mechanics, you measure the mass and you just insert it. It's like comes out it's just there, okay? So we're going to set that equal to 0, and he applies the operator. He converts the operator to the fully covariant operator that applies in curved spacetime, right? So you end up with the spin-affine connection in there, okay? So, and you end up with what I call the Dirac-Sachs equations. So using that, you can actually apply gauge covariance and recover the Dirac equations from that, okay? So basically, you now have a field theory that describes inertial matter, okay? And that is fully compatible with the Einstein-Sachs field theory or set of equations. And I just want to go over, because I know this for a lot of you, this might be coming out of left field. Okay, Curtis, you mentioned lateral thinking, but this is really, everything is different here. So what I want to say is that, okay, the experimental part of quantum mechanics, right? Remember, quantum mechanics is not descriptive, right? It's empirical. So it's not claiming what's going on. It's saying there's a probability, and then, you take a measurement and you get a result, and there it is. And you can match it, with the probability that as you do the measurements a bunch of times, you can make a plot and it'll match up the probability. So that probability interpretation is not compatible with this theory. This is a fully closed kind of field theory that doesn't need a probability interpretation. And I want to mention as well is that no matter what anyone says, these probabilistic interpretation of quantum mechanics and general relativity, because it is a field theory, okay, it's an analytical theory, and it's not restricted to square integrals like the probability mathematics. So they're not compatible, right? And you really got to think for yourself about these things, okay? So the other thing is, like Noether's theorem applies here as well, is that in the theory, in the field theory, there's no separate particles, and there are no infinities. So you get fields and field equations, and they could be complex, right? They're spinors or quaternions, so they have a lot of nonlinearities, that again makes it incompatible with quantum theory, right? The nonlinearity and the linearity of quantum theory. One of the things that's nice about quantum, you can compute to your heart's extent. I mean, heart's content. You can actually do a lot of computation with the probability distributions and come up with really great results. But it is a linear theory. Now, that being said, what we just did in the previous slide basically made that linear theory nonlinear. But the result of that is, in reverse, you can take that nonlinear field theory and you can have a low energy approximation, and you fully recover the Dirac equations and all the predictions from quantum mechanics. Okay. So basically, at this point, you have a apparent unification of not just gravity and electromagnetism, but also inertial mass. So with this set of equations, and you'll notice on the right, you have, I put this set here. This is the one I prefer to show. There are other ways to show that, but you know, it does have the spinifying connection, which is this little guy here, and that's what couples here. That's the coupling that you end up with. So let's move on. Some consequences of that full unification. I'm just making a list. You know, Sachs, he did a lot of work, and I know I'm going through this fast. I'm hoping that we can have some discussions, and I can answer questions. So he did a lot of work over his whole career. Published quite a few papers, and there's a few books that cover this, and so he covered quite a bit of different things and results in particle physics and cosmology. Now, the thing that I personally came to realizations of have to do with one of the results of this, and I'm not showing it in detail here, but one of the results of this theory is that when you have an electron and an anti-electron, a positron, and they couple, the ground state of that coupling isn't positronium. It's actually a coupling where the energy state is 2mc squared below the uncoupled state. So basically, you end up getting you know, gamma rays out. You get some an electromagnetic energy out that's equivalent to twice the mass of one of the particles, right? And so that coupled state in this theory, because it's a field theory, and these fields and their electric charge and their how they interact with space-time, right? That spinor coupling, the fields remain. The mass fields remain in this theory. So that's the one right here, the background pairs, that I'm going to focus on in the next slide, and will be the discussion of, you know, where does this come from? So first thing I want to say is that up until seeing this, I had never really seen a theory that could predict the mass of an electron from first principles. Basically, what we just went through. Okay. Now, there is an assumption of the density of the background pairs being a molar amount in a molar volume. I don't think that assumption is that surprising or that troublesome, but that is there. But you do end up with the mass of an electron in the theory, predicting it basically from these equations. And in addition, because of the Spinor formulation, you end up with basically these mass doublets. So the electron, if there's an electron, there's also a muon, right? And so in the theory, you can derive the mass of the muon as well, and you know it's like 206 times the mass of the electron. So that comes out. One of the things that I early on, like when I started realizing these things, I did my own computation. One of the things I was always kind of wondering about is the redshift. Like I always wondered, okay, there's two ways you can get redshift in relativity. One is, of course, you can have motion, right, velocity. The second way, though, is with a mass, right, gravitation. So I thought to myself, well, let's say the universe did have this permeated dark matter. What would happen with light if it went from point A to point B? And when I did that calculation, right, basically you can calculate that. The mass, the density that I got, given the Hubble redshift, was the same density that Sachs uses to predict the mass of an electron. So for me at the time, I don't know how many years ago that was. That was quite a while ago. When I came to this realization that okay, there is a background, there is something, right? There is dark matter. There's something that permeates everything, and that is what gives that exact number, gives us the redshift and gives us mass. You know, of course, my calculation could be wrong, right? But let's say it wasn't. That's, to me, that was profound. Okay, and you can see the list here. Spiral structures of galaxies falls out of it. And one of the things I want to say, I didn't cover electromagnetism as much here, and the details there, but Sachs does the same kind of recipe where he takes electromagnetic equations and does a quaternion formulation of them. And with that quaternion formulation, he ends up with more than what you get with traditional Maxwell's equations. So you end up with other phenomena that describe things that happen with particles that we see. And so I'll go on to the next thing. So what are we? Here's one that didn't. Okay, that slide messed up a little bit. So what are the applications to propulsion, right? This is the kicker here. So first of all, reduction of inertial mass. This is one of the things that I came to realize early on as well. Like, this was one of the things that I thought was, if this theory was correct, is going to be very powerful and very dangerous result. Okay, it's not something that you just want to do. It's a serious matter. Okay, so reduction of inertial mass. So earlier I mentioned that the background pairs, Sachs uses that density of the background pairs, a molar density and a molar volume, to derive the mass of an electron. Now, the background pairs, there is a way to split the background pairs. It's you can look it up on Wikipedia. It's called the Brett-Wheeler process. And basically, initially, you take gamma rays that each have the energy, same energy of an electron. They collide, and you get a pair production, right? So in Sachs's theory, that pair was there in the gas, in the background pair gas, and that, basically that uncoupled the pair that was already there. In the conventional theory, it said that energy is converted to mass. Okay, so which one makes more sense? Well, after, I was taught, energy is mass; they're interchangeable. But logically, energy is not mass. Energy is more than just mass. There's more going on, right? That's why there's the c squared is there. So anyway, so in this, it could, either one could be correct. Now, we all know there's quantum field theory. There's the prediction of the vacuum, right? Energy that's just like randomly popping in and out. Things are randomly popping in and out. And it sounds a lot like the background pair gas, right? But the background pair gas, there is differences. Okay, there is differences in what you're gonna have with those things that we can explore in the future. So anyway, getting back to the background pair gas. So let's say you're able to lower a volume in a volume, lower that density. What the result would be that any matter in that volume would have reduced inertial mass, and per the generalized Mach principle, would also have reduced charge, reduced magnetic moment. So what that would mean is, if the generalized Mach principle is correct, then you have an atom in there, and the atom would retain its form, right? It wouldn't just fly apart or whatever because mass is changing only. No, all aspects of matter would have to correspondingly get reduced. So how would you lower the density? Well, if you could use the Brett-Wheeler processes in a shell, right? In the outer part of a shell, you could lower the density in a volume, right? You might have to move it around. I'm not sure. But you could lower that. Now, thinking about the background pairs, and there's been a lot of talk about, I heard earlier discussions of electromagnetic high energy processes where you get, let's say, rings of electric fields and magnetic fields interacting. All that could very well be something that is compatible with this. I have not looked into that in detail, but like I said, this is a Spinor formulation, and from what I've seen out there, have been I wouldn't say Spinor formulations, but let's say Grassmann or other kind of similar mathematics used to derive equivalent Maxwell theories that result in those kind of effects. But anyway, so this issue of or this potential of the theory describing a shell where you're using some kind of effect where you're basically splitting background pairs, and when you split a background pair, right, you're going to get a pair. You're going to electron and a positron, or a proton and an antiproton. So there's a lot of energy involved potentially. Now, if you look up the Wikipedia page, you'll notice that there's something called the nonlinear Brett-Wheeler process, or the multiphoton process, where you can have like a laser field, basically a laser shining, having in a volume where you have laser light kind of in the entire volume at higher energies, and you shoot like one gamma ray instead of two, and you can get a pair production. Okay, so there's multiphoton or other ways, and that could potentially be what could be happening in matter. And I know there's with the recent resurgence of UFO discussion, of course, there's a lot of talk about, okay, what could be going on? Well, and the observations that happen, a lot of them look to me like it could be this kind of effect where there's a shell and the background pairs are being split, and so everything within that shell, the inertial mass is just reduced proportionally to the reduction of that density. Okay. Now the next thing that I came to a realization with in this theory that's potentially relevant to the discussion here of the alternative propulsion is propellantless propulsion. So Sachs theory, if you have a background pair, right, you have an electron and a positron. If you split them up using the Brett-Wheeler process, and that gas, well, first of all, let's say that gas has to permeate the entire universe, right? So basically, all of space has that background pair. And personally, I like to think about it like it's an ocean, right? It's an ocean, and we're just the waves on the surface almost. Like that's kind of the thing that comes to my mind. And you have an ocean that has a depth, right? You reduce that depth and have almost nothing there. Now the wave equation, right, of your velocity no longer applies, right? You're down there. You don't have the same constraints. If your depth is zero, you just have a bucket of water. You can move it as fast as you want, right? So now, okay, so now you have space permeates this, and if this particle-antiparticle pair gas is there, let's discuss what's going on with ordinary matter, right? So ordinary matter is dissociated, right? You have electrons, positrons, neutrons, which are electrons and positrons, together, coupled with positrons, and you have atoms, and here we are, right? We move around this gas, and nothing really goes on much. Now there's hints that the gas is there, right? So what are the hints? The hints are, well, the Brett-Wheeler process, right? You get some energy and something pops out. Another thing is if you have an atom with a nuclei that's complex enough, you end up with radiation, right? Radioactivity, where every so often the thing is unstable. So after a while, it'll just fall apart, and how is that falling apart? Like what's going on, right? So it's probably interacting with those background pairs in a statistical manner, right? That's why we get statistics with that stuff. So there are hints that background pair is there. Now, if we're trying to move through space, and we're traveling through this background pair gas that we're the waves above, if we can take as we're going, if we can take those background pair gas and use the Brett-Wheeler process where we're splitting them up, right? So there's some energy we're putting in, but we're splitting up, getting mass. You can set up an electromagnetic field that'll shoot out the electron, the positron will go the other way. Maybe you have a magnetic field that turns that around, right? Magnetic fields do not work, but they'll turn it around, and you can have another space where there's a positron, and you're shooting that out. Okay, so it's possible in this theory, if the background pairs are there, to create a device that will do propellantless propulsion. Now, what I'm talking about with the Brett-Wheeler process, if you look it up, the conventional ways to split background pairs and do this stuff require lots of energy, right? So this is why we're not necessarily doing it. And by the way, the set of equations there are the electron positron equations that solve the equations I showed previously in the theory, and unfortunately they covered up the words there. So that's the main. These are the two main consequences of this theory that apply to propulsion potentially, right? In reducing inertial mass, and if you're breaking up background pairs already, if you can direct some of them one direction versus another, all of a sudden you're moving like, you could just think about it. It's moving like nothing we would expect, right? And that sounds familiar, doesn't it? Anyway, so discussion. First thing I want to bring up, if this is all true, why isn't this theory popular? My reasoning is that its nonlinear theories are hard to use. Okay, so even if you look up general relativity, right, and you can ask the question, when people talk about dark matter and the reasons for dark matter in galaxies, and you look at their simulation of a galaxy, their simulations are using Newtonian physics. They're not using general relativity. And to me, that never made sense, because if you're going to say, well, that general relativity doesn't predict it, right, which a lot of people say that, they should be saying Newtonian mechanics doesn't predict it. But they say general relativity doesn't predict it, because they take the approximation of general relativity, which is Newtonian, and they can't describe those velocities of the galactic disks. Well, why don't they use general relativity? Because it's too nonlinear. It's very difficult. Now, there have been attempts to do that, and those attempts, there's controversies there, because when you're using a nonlinear theory, you need to make some assumptions, and so there's always a debate about it. Okay, well, that's not necessarily there, but which is worse, right? Postulating something by taking an approximation and ascribing it to the entire theory, it's probably better to say we're not sure, right? That's the real truth of the matter. And until recently, I feel like we didn't have the computational power. We just did it. Things, I believe, have become different due to the emergence of the ability to do deep learning. If you look at deep learning, and if you look at the mathematics there, it looks a lot like the same kind of equations that we had before, where you're taking covariance, and you're having very complicated, you're having differentials, and they're coupled, and there's a lot going on. So I think because of that, we probably have the computational power to actually use this theory and make some predictions, and that are more than just kind of like the making assumptions and the way that's been done in the past. So path forward, what I decided to do is I'm going to be starting an open source repository. So I think I'm probably going to use GitHub or something like that, And there's Python tools like SymPy, which can do. It's kind of like Mathematica. It can do solve equations analytically, symbolically, and also Jupyter notebooks, right? So it's basically they're open source tools, and I'm hoping to make a website where people can go in there and they can use it and contribute. And so I'm looking for collaborators if anyone's interested in doing this, because there's quite a bit to do. And I think it would be good to explore full covariance and what it actually leads to. I think that got cut off as well, the last line. But I'm interested in finding experiments that can be done, or actually other predictions that Sachs didn't cover, and maybe redoing some of the stuff that he did, but using a computational approach where we can get closer predictions or more exact predictions. So I'd like to find an experiment that can confirm, what's going on here, because it's not because things are so similar, right? It does quantum mechanics, basically the mathematics of quantum mechanics pop out. Because of that, it's not straightforward to come out with something that differentiates. But in terms of the interpretation of what's going on, we should be able to find things that differentiate it, right? So if the background pair of gas is there, and we can reduce it, and we can get propulsion from it, which the Mach effect could be one thing that's one thing that's happening there. Could be what I just covered. It could be that, we don't know. There could be other things happening as Jim covered. So that's that. So Mach effect lab update. I'm going to cover two things. The first is there's an experiment being done in the air. Okay, it's on a linear rod. It's not at Cal State Fullerton, but one of our collaborators, Michelle, she is running this. She's up in Colorado, and she's doing this experiment in air. And what she's doing is instead of having we have a torsion pendulum which goes back and forth when the device moves, and so that can introduce nonlinear Newtonian kind of effects, right? So what she's doing is she has a rod where the device is mounted, and it's a pretty heavy rod. It's much heavier than the device currently. And she's gotten a lighter system in, and that rod is on air bearings, so there's very, very low friction. Okay, so that gives the device a chance, because it doesn't produce a significant amount of force, but enough to actually move that device slightly. So she's getting a lighter system, and we're hoping that that device continues to show an acceleration, and that's where we're at right now. So I want to make a reminder is that if you do the Mach effect experiment in air will always be questionable. So there'll always be an issue. So whether it's the air pumping, just being pumped out, or maybe if you have a flat surface on one side, there could be standing waves coming up, and that could cause an effect. So you need to be very careful if you do this in air, and it's preferably done in vacuum. Now, in vacuum, if you want to have a very low friction bearing, that's difficult to do, right? So you could have ball bearings, but they're susceptible to the vibration. I'm looking into using sleeve bearings that are low friction, but I don't know if they're low enough. We may end up having to use magnetic bearings in the vacuum if we're going to do something like this. So, like I said, a lighter system is on the way, and preliminarily, this is one of the runs. You can notice there's two graphs here. One is a Philtech sensor that's on the end of the device that's measuring, and another of these lines is a video, something called Tracker, that looks at the registration marks that are on the device. There's one that's looking at the device that oscillates, and then one that's looking at the entire structure. And you can see the entire structure moves with and the device they move together. And so you actually are getting a small motion in one direction only. So I'm really excited. I'm hoping that, you know, when the LiDAR system comes in, that we'll get a curve that kind of matches this. Now notice that there's a lot of discussion in here of what's going on, but basically what's happening here is there's kind of a sweep over time of different frequencies, and the device will go in and out of its resonance and where the effect is. So that's why it's not, you know, initially it doesn't necessarily move, but once it hits the effect and resonance, you'll see it kind of going off to one side. So that's the initial, and I'm hoping that in a few weeks or in a month I can give an update to where we are with this. Now the second update is what's happening at the Fullerton lab. So we took our Quaternion GR Welch vacuum pump, the roughing pump, to the manufacturer for servicing last week, and they fixed it. So I'll be picking it up next week. Our turbo pump is operational. I've calibrated the Pirani gauge, and I've replaced the large rubber hose that was in the system with a stainless steel bellows. So between the turbo pump and the chamber itself is all going to be steel tubing and bellows. And so the new vacuum system should allow us to get below 10 to the minus 4 torr. And that's one of the issues that I had with when I first joined was, you know, the experiment was being done on a pendulum in air, and I was not in agreement with that. And eventually we figured out, yeah, that isn't a problem, and it's back in the vacuum. And even the vacuums we were getting when it was like a few millitorr, that's still too high, right? If you look at what's happening on Mars, there's a helicopter, right? Who would have thought? So, so we need to get that vacuum as low as we can to be able to rule out air effects, okay? And this is a recent graph, and this was done at about, I think it's about 3 torr. And this is a sweep from 41 to 31 kilohertz. And you can see, and this is over 40 seconds, so it's quite a slow sweep. The function here, the signal generator has a ramp, 90%, so 10% up, 90% down. And you can see as it sweeps through the different frequencies at about 33 kilohertz here or so, you can see that the device, the green, I believe is or aqua, is the device through tracker, through the video, and red is the Filtech, which we have on the other end of the torsion arm. And you can see they both move in unison in some places, and in some places they move opposite. So if you were only getting Newtonian motion, you would see opposite movement, okay? And if they move kind of in tandem, where one's pushing the other, you would see them kind of going together. And that's what we do observe in some portions of this motion. So you can see clearly one goes down, one goes up. That's clearly Newtonian vibration of the system, right? This is going down, that's going up, that's Newtonian. As we go along here, you end up getting places where the resonance is hit and the device is, you know, the effect is coming out. So as I said, I would prefer the other method where it's linear. So we're discussing that, how to do that in the vacuum. It's not, like I said, it's not straightforward. We can't put air bearings in there. If we use anything magnetic, that's going to be questioned. We're trying to find an alternative way of supporting the system and maybe making a linear result. Now, one of the things I'm thinking is that if the result Michelle is getting is good, then maybe we can try to put magnetic bearings there and see that the magnetic bearings work on air and work. If the system works in air with magnetic bearings and air bearings, then maybe that'll justify, and the behavior's exactly the same as predicted, then maybe if we do it in vacuum with the magnetic bearings, maybe that'll be an acceptable way to rule out magnetic effects from magnetic bearings. But like I said, I prefer to find something that's, you know, a way of supporting this at low frictions without magnetic bearings. if anybody knows how, let us know. We definitely try to apply that. Discussion, future plans for the lab work. Like I said, we're trying to get. I'm trying to figure out how to do the same kind of experiment where the thing is just moving in one direction, and you're showing that without a back and forth motion, without a potentially nonlinear effect of a pendulum type motion going on. Also, we're talking about maybe figuring out how to get signals to the device, because right now we're doing sweeps and we're using a signal generator, and there's no the way it's set up currently, there's no potential for feedback. So I'm looking for ways to optimize the signal I'm sending to engage the phenomena, engage it to start moving without having to do these sweeps and just look at it for a short time. So I'm hoping to be able to use some of the equipment we have in the lab to do a feedback loop where we're putting it in and we're adjusting, because as it operates, the temperature heats up and that moves the resonance. So we're going to be trying to figure out a way where we can keep it moving for extended periods of time. So that's about it. I think that's the last slide.
Wonderful, Curtis. That is tremendous, man. That is absolutely tremendous. Let me take the slideshow down. Let me bring in the usual suspects here. Mr. Sokol is with us too. Everybody, please give Curtis a tremendous hand for an awesome update. Thank you, Curtis. Thank you so much. Thank you so much. So we have about 4 minutes until the top of the hour. Does anybody who's on the call now have any questions? There's Jeremiah. There's the hand. And then Mark too. Oh, and Jared. Look at that. Okay, well, Jeremiah, go first, sir.
I can't even ask this question without first saying, what an incredible presentation. I never thought that anybody would be realistically getting into the positronium states or the background positron electron gas. I wasn't even aware that in Sachs theory this existed. I had a wild vision as a personal experience where I've viscerally seen this in front of my eyes unfold, and I thought I was totally off my rocker. But apparently this has happened many times, and far brighter minds have already identified this. But thank you so much for bringing this up. And so my question is, in terms of low energy separation of the positron electron background and bringing these points out, if in fact they are already there, which is what we theorize, and you separate them out of that physical space-time, would that not cause a contraction or what we call a negative energy state, which would basically be that negative energy in the Alcubierre warp drive that's so called for producing the other side of this warp bubble? I'm just curious if you have any ideas on that.
So in Sachs's theory, like I said, it's a field theory that's kind of strictly analytic. So there would not be any negativities. And if you go look at his work, he basically says that when you're at the ground state, which these pairs are, you're at zero. Everything else is above that. So there's no negativity. There's no negative. You're at zero. That being said, remember, this is a very nonlinear quaternion theory. So we're not talking about positive and negative anymore. It's more. It's right. It's the real I, J, K, right? You're shifting off. So keep that in mind. But also, if you're doing that, like remember the generalized Mach principle, you're actually changing, like I mentioned, in a volume. If you're lowering that density, you're changing not only the mass, but the charge and magnetic moment effects of matter. So everything will still be what it is as it interacts. So those other theories, the issue is that, they have to bring up those things, but it's not consistent, right? The negative energies are necessarily consistent with Einstein's field theory, strictly.
So as far as what you're saying, there's no competition here between what Sachs is presenting and Einstein's general relativity, where these are actually compatible things instead. So we don't need to incite new terms like negative energy to explain what's going on here at all. Am I understanding correctly?
Yes, yes. In fact, Einstein's theory, like I showed on the presentation, is you recover that from Sachs's field theory. So, you know, like I said, with Einstein's theory, you're really having, you know, 10 equations, and you have something that is reducible. You know, it only has 10 unique equations instead of 16, which is what is expected if it's fully covariant, right?
Thank you. That answers my question.
Yeah, again, absolutely remarkable. Absolutely remarkable. Curtis, thank you so much. So Mark, what do you have, sir?
Actually, this idea was inspired by Jeremiah when he was down here, but I heard your problem with a low friction bearing inside of a vacuum, and I couldn't help thinking of this ingenious idea that Jeremiah came up with when he was down here. If you have...
Oh, Mark, you're breaking up a little bit, sir. Now you're breaking up a lot.
It must have been good if he got cut, right?
It was, yeah, it must have been that good. It's suspense. See, and he doesn't even know. Okay, you cut out.
Your whole question again, Mark, because you literally got cut right at the point where you were about to ask.
It was a cliffhanger. It was cliffhanger.
Okay. Actually, Jeremiah already knows this, but if I was just giving you a suggestion of what to do to minimize friction for your pendulum inside of a vacuum. If you have a large magnet, like with a flat surface, and you put a ball bearing underneath it, there's threaded ball bearings you can buy. The ball bearing being attached to your pendulum system, you can add weights underneath it or add magnetic flux to bring it to a point where it's about to fall down, so it's barely touching the magnet, and that will drop your friction to as low as possible and work in a vacuum pretty well.
Okay.
Yeah, to clarify too, what he's talking about here is there's a perfect balance between the center of a single pole of a magnet. So let's say you take a disk magnet, for example, and you go exactly to the center. If you place a ferromagnetic ball bearing there, instead of that ball bearing being attracted straight to the surface, what will actually happen is it will rise up off the surface because it doesn't want to be attracted to that center point. It's pulled to the right or to the left. And it will easily hover itself there frictionlessly, but be quite stable so long as it's oscillating. So even if a tiny oscillation at piezoelectric frequencies, say 48 kilohertz, it can easily suspend itself there frictionlessly, and it works quite well.
Well, guys, let me
use round a sphere and a round magnet.
Guys, we are still at the top of the hour. We don't have a ton of time. I'm wondering if do you think we could come back to this during the lab during the lab session and go? Would that work? And then what I want to do now is, if it's okay, I want to go to Isaiah and hit on the Searl Effect Generator, because again, okay, well let me do that then. We will come back to Curtis' work in a bit, and that way we can kind of stay on schedule. Let me take everybody out again. Curtis, tremendous presentation. Today, this is one of our best APEC sessions. I am so excited. There's Mr. Riss with us. So, okay, so let me take everybody out back into the studio, and then we will go to Isaiah. Oops. Okay. Sorry about that. And, you know, I should probably preface this by saying, Isaiah, Jared Yates is the fellow that you know him much better than I. And Jared started telling me several months ago, he's like, look, I know this guy. And I'm like, okay. And he's like, no, you don't get it. He's like, he's doing a Searl Effect Generator, but he's doing it by the book, like the way that it's actually supposed to be built. And he started describing what you're doing and the precision. And I just, like, my eyes just kept getting bigger and bigger and bigger, right? So, because, like, I mean, for probably a lot of the people in the audience know this, Godin and Roshan did one, but they used a gearing system in theirs. Paul Murad did one, but they ran into machining issues, and so they used magnet inserts instead of magnetizing things correctly. And so all of these replications have been done, but they're either partial or they're incorrect. So the thing that was exciting is, from everything Gerald told me, you're actually the only person who's doing it the way Searl said to build it, right? So, So if it's okay, let me see. I think is your presentation up? Do you have one loaded, or?
Yeah, I loaded it, the PDF at the bottom. Let's see, present, and Slides, it should be there.
Okay, I'm not.
There it is.
There it is. Okay.
There it is.
Okay, so I'm going to add this in, and Isaiah, let me. I will remove myself from it. Looks like you've got. Oh yeah, you have a ton of slides. Okay, and just let me know if you want me to take this down or anything like that.
Sure.
If you want to do a walk around, in the lab, that's also fine. I can take this down and you can show the camera. You look great. You sound great. So,
Excellent.
Thank goodness. Thank goodness. I'm not that familiar with using phones in StreamYard, but it looks wonderful.
Okay. Well,
Okay.
I just want to say thank you for having me here today and allow me to present what I've been building. So just for starters, my name is Isaiah Ritchey. I'm 43 years old. A few things about myself is I was born in Oregon City, and I've lived in the Woodburn area my entire life. I have no formal education. I was homeschooled by my mom and my dad. Except I graduated in high school with a GED. I immediately went to work as an apprentice to become a general contractor. I'm married to the most loving and supportive woman ever. I am now a general contractor and presently do remodel work all over the Willamette Valley in Oregon here. So a little bit of background as to how I got into this device and how long I've been into it. When I was in my early teenage years, I became very interested in the topics of free energy and anti-gravity. I followed a lot of Jean Louis Naughton's website back in the early and mid-1990s, plus reading anything I could get my hands on through my local library and online. When I was 14 years old, with the help of an electrical engineer, I made my first Tesla coil, plus several other magnetic type devices. I have had an interest in these type of topics basically all my life. Eventually, when I was in my late teenage years, I gave up on inventing and exploring this type of field, but I always had a very insatiable curiosity about it. When I was 27 years old, I started having a feeling and an urging in my spirit, which I believe was God pushing me to start getting back into inventing and creating things like what I was doing when I was a teenager. One morning back in 2008 of January, I had a dream and I saw these interweaving linkage arms, which I thought represented energy fields stemming from a central core. I had no idea what this meant. Like I said, I hadn't been into that topic in quite a long time, but I went with my intuition and began researching free energy and over unity devices, having no idea what was going on in the world back then. With this type of technology. I quickly found the videos that were put up in 2007 about John Searle, and that he basically had made a re-emergence and had made a mock-up device of his SEG unit. I was immediately fascinated and thought to myself that this would be an easy project to create and make it work. It looked extremely simple, right? But within a few months of investigating this new technology, I ended up finding one of the images that they showed on their website of the magnetic field of the device, and it was almost exactly identical to what I had seen in the dream many months before. And so what began in early 2008 and making tons and tons of mistakes and lots of successes has now grown into what has become my life's work. So basically, for introduction of what I have come to understand what the SEG is, as you can see in the slide here, you have the first unit surrounded by induction coils and the 12 rollers connected to the device. And then below it, you have the 3-ring system, which is basically a full working SEG with a full set of rollers. The SEG is basically a converter of ambient energy. It's not over unity because you're not putting anything into it. And what Searle claimed was that in later devices, actually his first device and in later devices, he was able to have them fly by inverting gravity. The basic SEG in concept is 4 layers, like seen in this slide here. The first unit, it's 4 layers. You have the inside layer, which is neodymium, the outside layer, which is an insulator. I use Teflon, that's what Searle used. And then the third, which is kind of the gray colored, is a magnetic layer. And then the 4th layer being pure copper. And then the 12 rollers on the outside, each roller consists, and I could show you here, it's easier. Each roller consists of 8 segments, and they all have the same elements as in the main stator unit. There's 12 of those together, so there's basically 96 slices. So let's see. The purpose of the SEG is to, for what I'm doing, is to use it to create power, generate electrical energy. Let's see, I'll go to the next slide because that is more of my story. So like you have in a water dam, you have a reservoir, and the water dam, the water channels through the dam itself, the hydroelectrics, they turn, they produce power, and then the water goes back out towards the ocean, evaporates, and then goes back into the system. So it circulates. So it's similar with the SEG using electrons, is that the center core is neodymium, which is a rare earth. And the electrons from that source go out to the rollers as they rotate and then to pick up coils. It's basically a type of toroidal effect, as I understand it. Below, you see the law of the squares, which I'm still learning a lot about, that John Searle came to understand through his own dreams. And those represent quantities and proportions. So you can see in the lower left-hand corner of the squares, it's 4, 7, 10, and 13. Those are the weight portions, the beginning weight portions of each roller, representing grams. Let's see here. So it's easier for me to just show this. So in each roller, you have a center core, being neodymium. That one would be 13 grams exactly. So I have scales that are really accurate. So 13 grams exactly. And then you go to the Teflon layer, the white plastic layer, the insulator, that one being 4 grams, and then the magnetic layer being 10 grams, and the copper layer being 7 grams. So they all have to be weighed very precisely, machined very precisely. And the main stator body is also weighed in a similar process, except each 4 layers, they all weigh the same exact amount. They're not layered, they're not weighed like the roller is. Next slide. So this is another one I grabbed from their website. What John Searle believed was that magnetism was not a cousin, but is similar to light in that it had bands like light. The white color of light has multiple bands, and when all combined, you produce white light. But when you run it through a prism, the white light that goes in splits the wavelengths, and you can see the colors. So he believed that if you could isolate a certain bandwidth in the magnetism, you could pull out the electrons from the neodymium instead of smashing the electron, or not smashing electrons, smashing things like in you have in nuclear bombs. They smash the atoms and it creates an enormous explosion. He wanted to basically just tap the neodymium and ease out the electrons with magnetic fields. So these are another slide from their website. A lot of the squares showing the proportions of the different elements. So what I've, because of, it's kind of like miniature or amateur detective work through all these years, learning the weights, the correct weights for the stator. It's what I got from Fernando Morris, who is, as far as I know, still working on the SEG, is that the main stator parts, each one, need to weigh 2,854.2 grams each. And so, unlike the rollers, each one of those has to weigh the same, and you can see the portions in there of the main stator body. Below is a representation of what the magnetic field lines may look like. I'm not copying that picture exactly, it's just a representation. So this was a major clue that I stumbled upon quite a while ago, and with every single replica I've ever seen of any SEG, except for Fernando Morris, who was tutored under John Searle, they basically keep all their magnetic fields, all the other people have done replicas, they keep all their magnetic fields in parallel, and they don't do anything radially. What Searl said with his device is that he used perpendicular fields, so that on the top picture there, you see the roller going around the main stator body, and what every other replica I've seen they do is they just keep the fields all in parallel. But what Searl said was one of the keys to his device is actually having perpendicular fields, so that the stator is actually radially magnetized and the roller is axial magnetized. The picture below it with the points and the weave lines, the magnetic field lines coming out, that is one of the rollers that we're working on presently, me and Gerald. So that it's actually magnetized and has points coming out perpendicular. So that's a work in progress, which we've had some success in already. So this is another illustration. I've had some success with basic magnetizing the roller segments to produce weavy lines instead of just straight fields. It was back in 2015, which I'll get to that slide, that I worked with another guy, and he had a pretty decent magnetizing setup, and we were able to create weavy lines on a magnet instead of just straight. So this is just a representation. This is another image of from the Searl's website showing AC and DC fields magnetized onto the layers. The middle image is showing the radial magnetization and the axial magnetization on the rollers. And then I believe this black and white image below was of one of the roller segments that was magnetized in Germany. I think it was back in the 80s. It was before they had all the green film and everything, so they just used iron filings. But it seems to indicate that there's 34 distinct points of magnetism on the ring roller. And this is the design I came up with because I had a dream. I met Searl, and he told me about that it's a magnetic matrix. So I came up with some images. The first one with the red and black is a possible way of magnetizing the stator segments, because there's 12 sections on the stator to compose the magnetic ring. And then the matrix he talked about was kind of what I perceived in the dream he was talking about. And let's see. Oh yeah, so this is my first attempts at building it back in 2008. I believe it, excuse me, was back in the mid part of the year. The top image was one of my very first electromagnetic coils. Again, I was just trying to copy the original device that was posted online in 2007. And the bottom picture is of the Teflon rings. I was just using nylon or Delrin at the time. And then in 2008, December 21st, I made my first roller. I had to hand grind with my lathe and the Dremel tool out the ceramic magnets, and they were just too crazy weak to be able to support the weight of the roller. So I used magnetized neodymium magnets. I'm sorry, neodymium magnets for the center to be able to hold it to the magnets behind that aluminum plate. And so here I was showing the eddy currents on the stator, the copper stator, and that when basically you hold them parallel, they do repel each other, but it's easier to demonstrate this. They do repel each other, but when it's 90 degrees, it's much more stronger. So what I'm still working on is creating the roller that the magnetic field is going axially, but also has points that come out so that it acts as a magnetic bearing. Now, this is one of my roller segments in March of 2009. I was still hand grinding all the ceramic, and I still have those pieces to this day. So that was my very first unit back in 2009. It was very, very basic. I had not figured out that I could order the magnets from China and have them all precision made. I was still doing everything from scratch. I found a company in Salem that would make the copper bands for me, and they did a fairly okay job. I had all 12 rollers, I think there's 12 on there, 12 rollers together, and the center was a neodymium magnet, which helped hold everything together. Again, I wasn't working with pure neodymium, as I've learned I should be now. It was just neodymium magnets in the center cores. So there's another picture of it. At that time, I was working pizza delivery, so I took it to my job to show everybody. I never got that one running because I never put the time into developing the electromagnets. So it was just a stationary model at the moment. Here's another shot of some rollers. Some of them I did just solid sections, so they weren't like 8 sections. They were just solid tubes of copper with magnets stuck inside. So it was very, very basic. And there's the hand ground ceramic magnets. Because I didn't know about the suppliers, I could have ordered them from China, but at the time I just didn't know. So I was getting regular magnets from the hardware store and pull them out of the casing and hand grinding them. And I learned a lot about grinding and what to do and what not to do. So that's another view of the nylon with the neodymium magnets inside of it. That's the main stator body I was working on. And still working on the electromagnets with that version. Early back in, I think it was 2009, I was going back and forth with Fernando Morris, who is the lead engineer at Searl Magnetics, and exchanging, asking questions, and he was exchanging answers. But as time went on, he just stopped giving me answers, I guess because they became more corporatized and he couldn't share anything. But with the information he gave me, including hand-drawn circuit diagrams with all the roller specs and sizes and weights and voltages, was really nice. So it gave me a jump start on figuring out the circuits, the exact ones he used, and I still use similar designs to this day. I based mine that I've upgraded heavily right now off of his original designs. So there's one of my very first plans back from 2011. And there's a slide of my shop from 2011. It's very basic. Now these are ones, these are magnetic rings. Magicians will use them, but they were an easy way for me to start trying to manipulate the fields on them because they were high-powered neodymium magnets, and they were very, very cheap. They were like $1 to $1.50. So I could just buy tons of them. I could experiment with them, break them, whatever, cut into them, demagnetize them, magnetize them. They were fun to play with, and they were a cheap way to play with magnets. Now this one I just made for kicks. It was never supposed to run, and it never did run. This was my version of, I was trying to make something like Tony Stark's arc reactor in size, so I made a miniature version of a Searl Effect Generator. I put it on YouTube. It made a lot of hits. People really enjoyed it. It never ran. It was just for looks only, but it was all magnetized. I weighed everything correctly so that all the layers actually weighed the same. The rollers were only about 1/4 inch wide. It was really cute. And that's another shot of it. So the slide below is, that's for another year. Sorry about that. Okay, so in 2014, I kept advancing the system, and I made a second ring. That one was quite challenging because it was much bigger, and it's not something I had a lathe with the capability to spin. It was about 18 inches wide. I still have that one down here. It was about 18 inches wide, so I had to come up with other ways to be able to create it and try to keep the grams and the weights as accurate as I could. So I still have that model down here. That one never got running. I just continued building like a third version. And so there's another version picture of this one. And it's where I started tweaking with the electromagnets and the rollers, and every iteration of this, there was tons and tons and tons of errors and finding what didn't work versus what worked. Okay, so there's more roller samples, the rings, the magnets, and then the Teflon pieces. And this is okay. So these are some basic plans I came up with, computer illustrations. These are mine. They're not published online. Just showing the portions and what percentages they are. Because basically with the rollers, what John still states is that they have a minimum gram weight that you need to start at. And that's the ones where it's the law of the squares. And basically from that size, which is basically this size, you can enlarge it to any scale you need. So I'm just going for the minimum. It's easier for me to work with instead of a very large setup. Here is some plans that I made because I was looking around, I believe at the time, for people who could manufacture them, and also for myself, so I would know the exact sizes. And at this time, I was experimenting with pressing my own powders. That way I could control the mixture. I could put in my powders what I wanted. I only had ferrite magnetic powder. And so I play around with this. I got a 50-ton press and I succeeded in making, let's see, is it here? Okay, so I did succeed, maybe it's further up. I did succeed in making my own magnetic ring. I never centered it because I think it was about that year, it was at 2014. I had another friend get interested, and he supplied me with some magnets that I still have to this day, neodymium rings that were machined to just the right size. So I didn't need to press my own powders. Okay. So this is another schematic that I drew. It was very basic, obviously, of directions as I understood them back then. The main stator body, from what I understood back then, was not radially magnetized. That came later on. But this was axial magnetized to the thickness, just using high-strength neodymium magnets. And these are some schematics that came from the manufacturer in China. So let's see, that's the 2014, that's the second ring system. And then in the lower portion, the lower picture, is a box of 1,000 Teflon rings that I machined within a few grams accuracy. That way I could later go back and get them scaled to where I just needed them to be. But I got about 1,000 rings made. I cut them all out myself. And there's another view, 2015. Started with squares and then machined them into the rings. Oh yeah, there it is. So that was my first magnetic ring I made from scratch with the shop press and the powders I got from China. But I gave up on it because I had the magnetic rings given to me. And so this was where I started working with changing the magnetic fields on the ring magnets. And these are my very first forms that I made with just out of a wild guess. And so these pieces would all fit together and the magnetic ring would be in between. I sent these samples down to my friend, probably some of you know him, his name is Russ Grease. I made a video and sent it to him, tried to get to his attention, and it got his attention. And I sent these pieces down to him in California, and he had about 12 different samples to work with, using all the way from I think 200 volts all the way up to about 2,000 volts at over 1,000 amps and 1.5 kiloamps, and then all the way down to where we were getting no effect, all the way to where it just washed the whole magnet out and made a straight line. But the in-between voltage, which I have it all listed, we were able to produce ring magnets with weavy lines that looked like almost like a snake or a wavy line. So it really did pan out and it really did work. Once I move the camera on, I'll show you the device I used to see those wavy lines in the magnets. But it did produce waves in the ring magnet. So those were the samples. There were 6 on each side. He just put those into a piece of foam. And then the image below you can see is the magnetic film on top of the ring magnets as they rotated on my jig to show visually that we could change the wave structure on a ring magnet. So just being perfectly straight, we could actually design a field and put it on there. So there's the jig I made. I still have it right here. I'll show you guys with a compass in front of it, and still using those little magic rings because they're very cheap, and I could just buy tons of them and break them or heat them, whatever. It didn't matter because they were very expendable. So there is another image of the wavy line. It would create a waviness in the magnetic film. Here is the 3rd generation SEG that I built, started back in 2016. And that's the one I have motorized running right now. And here is the main stator ring magnets for the SEG version 3. And now those had to be ground down, and I got it within about 0.2 of a gram accuracy. So it took some time getting those things ground. I actually demagnetized them, ground it down, and thank God I found a magnetizer about 30 minutes from me, a company that has one, and they let me use it to remagnetize them. That's local out in Clackamas, so it's real close. And that's how I put this whole system onto my lathe and was able to machine the magnets down, the stator magnets, to ultra precision, so within about 0.1 of a gram accuracy. And that's the jig I used to hold them all together. And there is the stator copper ring, precision ground and polished. There is one of the magnets that I was weighing, which is the magnets in this roller. So these images are from a gentleman I met and corresponded with quite a bit. English was not his first language. He was born and raised in India. His name was P.R. Jayakumar, a brilliant engineer who worked at a company with magnets and alternators and AC and DC currents. So he had some very conceptual work. So I've saved all his documents. Some of them are available online, and a good portion he sent to me are not available online. So this is just a sample of some of his work and his ideas of magnetizing magnets. These are my own hand-drawn, or most of them are hand-drawn images for some of the machines I was thinking of designing, the magnetizers and a custom-built lathe to manufacture the larger rings when I move into that, when I need to design them in the future. So here is one of the almost finished products of the Gen 3 Searl Effect Generator replica. The little ring magnets you see on the right side and the stator body on the left, and then the bottom image was the math that I used to figure out the circumference and the size of the rollers in relation to the stator body. And here on the 2018, it's one of the finished prototypes for the roller segments and then the stator body underneath. So most of these images you see here, or say some of them, are on my YouTube channel. These are just clips I took from my own videos. Let's see. And there is the finished product of Gen 3. What I was told, one of the ideas was to use nickel 200 for the inside cores instead of neodymium. And so I machined that out on nickel 200, and then 96 parts in the rollers for the inside layers, inside parts. It was an idea that we're still working on the ring magnets for the rollers. It would be magnetized north-south, and then putting perpendicular fields on the ring magnet. We're still working on that one, and it looks promising. So there, back in 2021, May 4th, the finished cutout versions of 96 copper rings, 96 Teflon rings, and 96 nickel 200 core for each roller. And the magnets aren't shown because they're all fabricated. They're just in boxes ready to go. So here currently is what I have. It's a capacitor bank I got from a website called Amazing One, and unfortunately they closed down this year. But I have this currently, and I use it sometimes for simple magnetizing experiments. It puts out 10,000 volts at max, and I have it right next to me here. So that's one we're currently experimenting with and getting some interesting results, which I'll show you guys when I move the camera around. So these are some of my one of my magnetizing coils. It's been quite the progress with developing these, starting from some very basic ones up to more sophisticated ones. So the top one had 6 points on it, so that on the ring magnet in here we could put 6 points, and we succeeded in doing that. And then the bottom one, the bottom image is for accurately viewing and measuring the field strength on the points and the magnets themselves, and also just viewing the fields with film. So the device on the bottom it holds a ring and then rotates at any speed we need, and we can put the Gauss meter, mount it, and accurately just hold it right exactly where we need it to go. So it's basically a testing jig for each ring, or a full roller, or sets of rollers if you want it to be. Here's a picture of basically all the coils that I came up with. Some were just complete whims just to see what would happen, and others were just trial and error and build upon to what I have now that actually is putting 6 points of magnetism on the rings. 3, I think. Oh yeah, there. So there is one of the very first versions I worked with back in 2013. It's the solid white with a black inner core with the ring magnets, and that was the one I many months ago I got first rotating around. The one where you see the solid Teflon ring with the neodymium core inside is version 4, and that one is not running yet, but I'm working on it. And then you see the other one with copper bands. One of those is working presently, so that'd be version 3. So here's a picture of one of the ring magnets me and Gerald worked out. It was his idea to put 6 points on there, so I worked on that and was able to put 6 points of magnetism on there with the coil setup we came up with. Here's one of the magnetizing jigs I worked on, and this one didn't work as well as I hoped it would. It was a top and bottom coil, and then inside you would put in a cartridge with a ring magnet, and I was hoping to get weavy fields with 6 points. It didn't really do much as the one that Gerald Yates, who's on here right now, Jeremy worked on. We had a single coil with 6 little pins in the center, which did a phenomenal job, and we were able to replicate I think it was 96 rings. We did a lot of them, and they all came out pretty concentric. So this is my first version that came out, and it was able to get the electromagnets. They're basically inductors. I got them all spinning, and the rollers probably doing around 60 RPM at best. It was the very basic model just to prove if the circuits would actually even work, and they did. So I hooked up blue LEDs because to me it just looked good having the blue effect with the red copper wire for the magnets, the electromagnets. Obviously this one is not to scale. It was just a demonstration unit to see if it could even get things rotating, but it did work, and so it paved the groundwork for generation 3. These I don't know where the idea came from, but I got the element pure neodymium and mixed it up with resin as a binder, and then cast it inside of the Teflon ring, so that I wanted to come up with a way to be able to use pure neodymium instead of a neodymium magnet or nickel 200. Frankly, because neodymium magnets only have about 34% neodymium. The rest is iron and boron, and I believe there's a little sulfur in there. So they're not pure, but I want to come up with a way that could have pure neodymium. The only drawback with this is they weigh about 3.5 grams, not 13, because obviously they're not pressed with 20 tons of pressure to produce a 13-gram object. But there are other avenues I'm trying with getting either pure neodymium discs or other types of neodymium, which Searl said is fine to use. He just chose neodymium. So this is Gen 3. This one is up and running with 12 rollers. All 4 segments in the stator are correctly weighed to within 1/10 of a gram accuracy. The rollers are generic so far in that most of the segments are pretty accurate, but as time goes on, I'm still getting them sized just correctly, but they're pretty close. They're just, everything is still parallel, like magnetized parallel to each other. So there's like the plate and then the roller. I'm not using any perpendicular fields, but on generation 4, that one is perpendicular magnetized. So that is the inside. It's an unmagnetized neodymium magnet. Again, it's only 34% neodymium, so it is experimental. And those were showing the poles on the roller. This is a slice out section of the electromagnet. I put these together. On my first unit, I used 14 layers of that. The one you see on the left side is a horseshoe shape. I used 14 layers. And on this Gen 4, I'm using 21 layers. So they're much bigger. They can have much more power. Here is the perpendicular Gen 4. It's the magnets for this version, Gen 4. It's perpendicular magnetized, and it's just a roller holding on to this to the side. I had these magnets made by a company in China, and they're within about a couple grams accuracy. They're very, very, very close. So I don't have to do hardly any machining work, which is really nice. This is just one of my schematics for the electromagnets. And that is Gen 4, which is sitting right in front of me. I'm working on presently being perpendicularly magnetized, and the rollers will all have the correct weights. And that is the end of my slideshow. So I want to go over real quick. This has been quite the most interesting project. It is my life's work. I've been on this for about 15 years now. And I have had so many coincidences, a couple dreams, and seemingly randomly meeting people. Oftentimes when I run into setbacks and running into basically these mountains of problems that I just couldn't get over, my thing is I would just pray and ask for the answers to come. And I've literally had it within hours to within the most being 2 weeks of the right person with the answer came into my life. It blows my mind every time, but it happened. It's been happening for all these years. Back in late July of the last year, I really just ran into just kind of a crossroads of maybe just winding this project up because I ran into too many problems I didn't know how to tackle. I prayed about it, and I was just like, I need to have somebody with the answers. Preferably, somebody I can meet in person. It's always been somebody online that would just approach me right out of the blue, usually with the answers. But I ended up meeting Gerald. And lo and behold, he just lives minutes away from me. And he has been the one, alongside my precious wife, that has pushed me and worked with me and given me the answers to the questions and the problems that I just couldn't see solutions to. He has been the answer, and an answer from God, I believe, an answer to make this project work. And without his help, I still would really be back where I was a year ago, just insurmountable problems. But see, my future plans for this device is keep working on Gen 4, keep experimenting, producing more and more upgrades, and working with a system that has everything machined exactly accurate as Searl describes. And with I'm kind of in like a detective. Just I got my feelers out there everywhere online looking for any details, and I continually run into people, even at totally random, they have little answers. I remember one time years ago I walked into a business meeting, and of all things, they were talking about positively charged elements, which neodymium it's a rare earth. That's a positively charged element. To the people that I have met, they have given me the answers, and now up to Gerald. So without continuing on talking, I'll see if I can flip this camera around, and I want to show you guys if it even works that way. Okay, so maybe not. So I'll just take the phone then and try to get it to work so that I can get a quick tour so that you guys can see what is actually working here. So this device here was basically the second version, not the one that I made in 2009. It was the second version. It's the one I used to show that the circuits could be built, the rollers could rotate around. Now these magnets were all hand ground and placed in here. They're ceramic magnets, and this is just a piece of acrylic and an old neodymium magnet. This is the generation 3, and there's been many, many iterations of these electromagnets. And so I hooked it up to be portable so I could take it to events or shows, friends, whatever. So I use a neodymium magnet, or sorry, magnets on the brain, and my Milwaukee battery to power it, thus making it portable. I don't have to plug it in. So I have a gauge here. So I just turn on without talking. Really, again, just want to thank Gerald for his help. So far, this doesn't produce any kind of electrical output, but it does prove how we can get the rollers to work, the electromagnets working properly, with everything being correctly cut in the right weights. So then over here is one of the magnetizing coils I'm working on. This is a copy of one of Searl's. Has, I believe, 22 layers of coils in there, and then the ring goes in the center. This is the one magnetizing unit I was speaking about with the removable core. Has a ring magnet inside with these points. And they put it in here up to the leads. This was another fixture that we used, having 10 points of magnetism. Cameras, I wish I could flip this camera around. This is a little awkward holding it this way. So these are more samples. This is one that I created from scratch. It's pure neodymium with a resin binder. This is one of the nickel. This is a custom made one from China, 34% neodymium inside. And then this is just an ordinary neodymium magnet. So I see when they're cast inside, this is the pure neodymium, and this is the custom one. This is the gizmo I was telling you guys about. If I can get this camera, there we go. That you can put a ring magnet in it and rotate it around. Now this one does have 6 points on it, this ring. And it's rotating around, and it causes deviations in the compasses as those points come around. So, oh yeah, there we go. You can see this. So there's 6 points on it. This is magnetic viewing film. So with Gerald's help, we were able to produce a magnet with 6 points on it. This is one of the stators. And then before this winds up, I'm going to get to question and answers here soon. So I'll just show you real quick. This is the Gen 4 device I'm working on now. This one will be all very accurately machined to all with what Searl states I need to do. So this 2854.2 grams, 2854.2 grams, the magnets and the copper will all weigh that same. Some of the modules I'm designing so that everything is, each module is independent to itself. It all receives the same power supply. It's filtered. And I have a whole set of ultra precision scales. This has 5,000 grams and it shows within 1/100th accuracy. And this one's for weighing just the roller parts. It shows 1/1000th of a gram accuracy. It's for weighing a medicine, actually. And I think I'll close it down. And if anybody wants to ask questions, I would love to answer them. And that basically just gives an outline of what I've been doing for all these years. And
Well, Isaiah, that is absolutely amazing. Absolutely amazing. Let me add everybody else back in here. Guys, a big applause for Mr. Isaiah Ritchey. Isaiah, it looks like 15 years worth of work. I have never seen an SEG that looked that large or nice, well constructed or precise. It's absolutely amazing. Absolutely. Yeah, so you know, before anything, I want to ask, have you seen any anomalous effects with this?
No, I've thought a lot about that. The only one I have noticed is that sometimes when I spin it up at full speed, my teeth start to hurt. And I don't know what that is with what might be in the air. I haven't noticed any kind of electrical discharge. Me and Gerald have measured for electrical discharge. So far, there's none, and I've also realized that's because it's one of the reasons it's spinning the wrong direction. And there's nothing unique about the magnets yet. We're still working on magnetizing stator and rollers.
Interesting. I almost wonder if that might be like a subsonic thing.
It could be. I've noticed a similar thing when I grind metal or powders that my teeth hurt. They get irritated, but I've noticed that when I'm in close proximity to this unit that spins up really fast, that it just bothers my teeth, like it bothers the bones.
Yeah, no, that's interesting. That is really interesting. Yeah, well, I'm definitely staying tuned. I'm definitely staying tuned. We want you to come back as you continue to build this thing, because, you know, I mean, it used to be the Searl effect was a hallmark. I'm not sure if everybody like watching knows, but for me, the Searl effect is like the prototype human-built anti-gravity device, right? I mean, you've got a couple of like archetypes, right? And T.T. Brown would be one of them, you know, but the SEG is definitely one of those core archetypes where if you say anti-gravity and you sit people down, they're probably going to describe something like Searl. So yeah,
yes.
I mean that, and it has such a tremendous history and legacy. I mean, Searl is one of the big ones, you know. Absolutely. So thank you so much.
One last thing, he actually wrote about me in one of his books. He wrote all those books, like I think 1 through 15 or something. I'll have to find it, but he mentioned my device and was very proud of it. And he was like, more people should be doing this. I was just like, he actually showed a picture, but that was in 2009. I was just like, he's talking about me. He showed a picture of that first device.
Well, from what I've read, he worked in a hat factory, right? And so he had lots of access to neodymium back then.
Yes, it was the glass company next door to the electrical supplier and builder. So he would just walk over to the glass company and get handfuls of neodymium.
Okay. Yeah. Sorry about that. It's been a long time. So yeah. And nowadays it's really hard to get, right? But you know, back then, yeah. So well, does anybody we've got a bunch of people on, and then we've got tons and tons of comments in chat. But yeah, do you guys have any questions?
I got
Gerald does.
I got some for Isaiah. First off, feel the bromance. Thank you so much for all the kind words, man. Yeah, y'all can see just how insanely dedicated to this mission Isaiah is. It is really inspirational, I think, to anybody who is working on their own projects to see what it looks like when you just put your full 110% into it. So Isaiah, rock on, man. The one other comment that I had was he mentioned his YouTube channel. If you guys want to keep track of his, you know, updates here and there as he does, Wood, Brass, and Glass. That's his YouTube channel.
So I would have to say I don't post too much on that. Because of the developments are going so well with this device, I mean, I can talk freely here, but I don't like to be very public with it anymore because of its nature, and I don't want to attract much attention at all anymore. So I really have been limited in the progress. But as like this forum, I don't mind sharing any details I have.
Yeah, that makes sense. Well, again, there's so much to it. I mean, and like I've gone through, it's been a long time, but I went through books. I went through Searle's books 2 or 3 times, and it was just like, it's very precise, right? And it probably, I'm sure probably everybody here feels the same way, but like it's so frustrating to see replications where they don't follow the rules, right?
Yes. Yeah,
And
most of them I've seen is they just don't follow the rules right.
yeah, you know, like and again, I'm thinking of like Godin and Roshan, and I think Paul might have done this too, where they basically magnetize plugs instead of magnetizing the rollers. I
Correct.
see Jeremiah's lifting his thumbs. Jeremiah, don't be so quiet. What are you thinking?
Well, I was just thinking, I really like the works that were done by that Russian team with Russia and Goshen, but also, Paul had a huge play in this, and it's one of the reasons why I think we all know Paul Merritt's legacy. He had deeply studied this, but I have never seen anybody else other than Isaiah do this so true to form. And all I can say is I think I can speak for a lot of the audience, just have been reading the comments the entire time. We're all so incredibly impressed that this has been done true to form and that nobody else has realistically taken this on at this level of accuracy and detail.
Yeah. For me, this blows me away. I mean, well, and Godin and Roshan, I believe they saw self-spin, and I think they saw it running cold, right? And
Yes.
again, they changed the formula. And then with Paul Murad, there was 1 or 2 points in time where they felt like it was losing weight. But, again, he changed the formula, and the way they were measuring it was really iffy. The thing was shaking around a lot, right? Because it wasn't a true SEG.
Paul was the first to admit that they weren't absolutely certain and didn't want to back up a claim that they had observed weight loss, but from everything that they had in their measurements, it sure the heck looked like they had a small percentage of weight loss.
There was a guy, Gerald knows of him. I talked to him and I got his circuitry about his device. His name was Mr. Delphin from near the Black Sea of Russia. And I talked to him several years ago, and he put out quite a few videos on YouTube. He didn't use the right proportions. His magnetizing was very unique, but in his last video, video 25, he got his pure neodymium to get down to negative 17.5 C. It literally went way below freezing. At the end of the video, he wiped frost off of it after just about 1.5 minutes of rotating the magnets at about 4,500 RPM. It just dropped in temperature. And then he had 2 more videos, and then he closed the whole channel and said he was sending the device to another laboratory, and that was the end of the story. And his email is gone now.
I thought he got shut down. I thought he got pulled. A lot of the channels that have ever done this kind of work, including Rescue, they all got pulled off YouTube. But apparently, I thought it was the algo pulling them, but I guess some of them actually stepped out voluntarily.
No, he's been scrubbed. He's been scrubbed. You try to find that video, and it is hard to find now if you don't already have it downloaded. And you can see, especially in one of Isaiah's photos there, he has a little thermal diode, a thermometer, digital thermometer, sitting on the center neodymium core there, because every time he's testing, he's got on his little digital readout there on the bottom of his device, he's measuring to see if there's any thermal changes whatsoever during testing. But since right now, we're stuck at like 200-ish RPMs, I think.
Yeah.
Yeah, and according to most of Searl's stuff, the good stuff doesn't start happening until about 550 RPMs.
Yep. That's what we're gearing up to, and why I'm enlarging. Gen 4 is a much more powerful version. I'm using 18 volt at probably 12 amps Milwaukee batteries, the big boys. Instead, I was just using these M12s, like 12 volts at 3 amps. But that's what I'm gearing up for, is a much more powerful system that can get up to way higher RPMs where the special stuff happens.
Yeah, and this isn't necessarily Searl specific, but I remember talking to John Darrer over at an R&D company called Sara, S-A-R-A, out in California, and they were doing experiments with all sorts of stuff, and then he worked very closely for a very long time with Jim Corum. And Jim Corum they called him the Tesla behind, or the man behind Tesla, because he showed how Tesla could have built all of those things. And one of the things that Darrer used to talk about consistently was nonlinear effects, right? Where, like in the case of the SEG, when you're below the RPM, you're not going to see anything. You won't see anything. And then once you start to get in that range, you may see small effects, and then you cross a threshold and bam, it immediately does whatever it's supposed to do. And
Correct.
he'd said that there are all sorts of effects, especially the strange stuff, especially the gravity modification type stuff, that are like that, where it's nonlinear. It's like you're going up an exponential curve, and until you get past the knee of that curve, you just don't see the effects. But it is one of the things that's interesting for me, though, is with the SEG for so many years, everyone said, "Oh, this is BS. There's no way that Searl could have been real," and yet, despite that, everyone who attempts one, even though they don't follow the rules, sees interesting, novel effects. And
Yes.
they see stuff that's a variation on what Searl predicted. So,
Yes. And I've seen that for myself, the things he said, and I just kept following up with him and following up. And lo and behold, I've been really impressed with seeing that so far with the experiments I've done, it has proved out to be correct so far.
Yeah. That's what I've seen from everyone I've talked to and everything I've read, right? Is there have been all sorts of debunkers that have come through and made all sorts of claims, and a lot of them are really logical, but none of them have been able to address the fact that anytime somebody attempts a serious replication, even if it's not perfect, they always see stuff.
Exactly.
So, well, let me see. I'm going through. Matthias Bage is saying, he says you must fix the waveform perpendicular in his parliaments on his parts. They're critical. Yeah. And I think a lot of this is probably stuff that you know, right? Obviously, It's a lot easier to know it than do it. And then I think one of the things that's like, for instance, neodymium is flammable, right? So you can't
if you
grind
grind it into powder, it becomes very flammable. But yeah, about 6,000 degrees. It's hot.
Okay. Yeah. And then you're just working with heavy metals. I mean, these are not easy to work with. This isn't pottery where you do it and you put it in an oven and it's done. This is like precision machining. So
correct.
Okay. Well, let me see. I guess if that's everything, let's give Isaiah another tremendous applause. And really, everybody who presented today, Tiziano and Curtis. I don't see Brendan anymore, but again, this is one of our best conference sessions ever. Thank you guys. Thank all of you. Tremendous. Let's go into lab time, and I want to start with Mark Sokol for lab notes, because Mark had a visit from Mulder and Scully this week that made headlines. Mark was in MSN News, and he was in the Daily Mail UK, and so apparently Mulder still hasn't found his sister, but he thought that you might be able to help, right, Mark?
No, it was actually something quite different. Let me show everyone the screen 1 second.
Okay, and I'll take everybody out except Mark, and then just let me know when the next person wants to go for lab time. We'll make things a little more mellow now.
Let me see if this works. Okay, there we go. Are you seeing my screen? Tim, can you see it? Tim?
Sorry, can you hear me now? No, Mark, I can't see it.
Can you see my screen?
No. Try clicking present.
I did already. It's on there. You have to.
Okay.
I think you have to allow it as a moderator.
Wait. Yes. Sorry.
There we
My
go.
apologies, sir.
Okay. Yeah. So the FBI showed up and they asked if I had any enriched uranium, and they apparently walked around the lab with a Geiger counter and figured out that I didn't. And yeah, that was kind of weird. And Daily Mail and MSN wrote a paper on it. But if you want more on the story, just read this. It's pretty much everything, kind of what happened. The most exciting thing that actually happened this week, other than the FBI showing up, was discovering this paper, room temperature hyperpolarization of nuclear spins in bulk. Now this sounds like a mouthful, but what actually they discovered is a way to increase the effect of dynamic nuclear polarization by a factor of 250,000. So normally DNO or DNP, dynamic nuclear polarization, is used to increase the NMR signal to noise ratio, and that can be done up to 660 times for hydrogen spins. But they found a way to do it 250,000 times at 0.4 Tesla. So that's magnetic field similar to what we're doing over here, and at room temperature. And this was done, they explain it in detail in this paper, but it was done basically using the special crystal that was made. They tried various different types, but it's a crystal made out of this TDPD material, which stands for P-terpolin, and that has 4 deuterium atoms added to it instead of hydrogen. Deuterium being the heavier isotope of hydrogen, and then it's dipped in pentacene, which is a 5-sided pentagon, basically 5 pentagons of carbon atoms with hydrogens around them. But those hydrogen atoms are all deuterium in this case. But even with the regular hydrogen atoms, you can see lower down over here, there's a factor of 100,000 increase. So what the reason for these crystals, the reason why you needed the crystals, was in order to create something that's called a triplet electron state. So they were pulsing it with light, and the light would go through the crystal and convert to a triplet electron state, which is over here. So you have the singlet, which is 2 electrons opposing each other, the doublet, which is slightly polarized, 1 unpaired electron, and then the triplet being 2 unpaired electrons. That is what combines with the microwaves inside of the chamber and increases the effect on DNO. So this is my main concentration right now. We're really excited about making this stuff. I contacted a company that they had used, which was actually in Milwaukee, Wisconsin, where Jeremiah lives. Sigma Aldrich over here, and that stuff will be coming in the next month or so. And when it arrives, we'll start building the crystals. The crystals are made using this method, the Bergman. This is similar to how large crystals are made for semiconductors. They have different temperature zones, and there's this thing rotating around, and it could be inside of a vacuum, or it could be done in or something like that. And we're going to need either some device that looks like this in order to do this, although it may be possible to do it inside of our vapor deposition chamber, which has very good vacuum capabilities as well as heating. One other thing that we'll need is the IPL light, the intense pulse light that will give us the energy to convert into this triplet electron state. And that is pretty much it for now. That's what we've been working on. We've also been doing lots of lab view setup for the lab. We want to get all of the inputs from these experiments going into one spot, and that's going to be a month-long ongoing project.
Awesome. And I see you have helpers. You have assistants with you today, sir.
Yes. We have Mini Mark here.
Awesome.
He's joining me at the lab.
Mark, that is so cool. That is so cool. Well, let me see. Let me go around the table. Let me go to Gerald, who has been adding a little bit here and there. Gerald, what do you have anything for lab updates to share? Look at his eyes. Look at I get to.
I was sick with COVID all week. I ain't got nothing, man.
Okay. Vitamin D3. I'm gonna push my vitamin D3 thing. That it helps. It helps a lot. Okay. That and a heavy coat, as you can see. Yes. Well, you're wearing one too. Yeah, it's that time of the year. What about Jeremiah? Jeremiah, do you have anything to share?
Yeah, actually, I did want to mention we actually have some pretty exciting news. So for quite a long time, we worked on reactionless propulsion drives. And reactionless is really a misnomer. Technically, there is a reaction. It just happens at such a small scale that in the far field, it appears to be a reactionless event. But I can at least say confidently we have propellantless repulsion at this point, and it came from the discovery of Gerald Tavares. Now, he's got a YouTube channel, and he's got some videos up of his very simplified drive. And what he's figured out is that there's a very interesting interaction between two permanent magnets with an orthogonal field interaction. And I personally theorized, though I may be wrong, that what he's really achieving is a dynamic nuclear spin reorientation of the dipole moments of those electron valences inside the neodymium magnets, and it's causing a slight change in the mass and inertia, causing this gyroscopic repolarized effect of reactionless force. But so far, he has a drive that weighs about 1,600 something grams, and it's deflecting itself on about an 8-foot. It's like a 7 or 8 foot tall 4-point pendulum by almost a foot to one side. It's a almost ridiculous amount of force. And just as a teaser, Mark and I are going to be working together to produce a dual rotor version that gets rid of the torque and just produces a pure linear force very shortly here.
Yeah, the parts are already arriving.
So I'll also mention, have produced a small version of that drive. It worked the first time. And the really interesting thing, and I want to bring in the non-linearity here, at 3,000 RPMs, my drive was producing a 3 millimeter displacement from its center position on the 2.5 foot tall 4-point pendulum. But at only from 3,000 to 4,000 RPMs, it produced a 6 millimeter deflection. So it doubled at an increase of 1/4 of RPM increase. So we predict that we could get 24 millimeters of deflection at 8,000 RPMs, which would be quite incredible. So if this effect is nonlinear, it looks like we have a real working space drive here, and it's all thanks to Gerald's discovery.
That's amazing. Amazing. Yeah, guys, this is awesome. Well, so why don't we do this then? I think that's it for lab updates. Why don't we go to open discussion? We'll just, but you know what?
Could we post a link too? I mean, for the audience, because it seems like we've got a lot of people that are so fascinated.
Yeah. Let me do that. Although before I do that, I want to show you guys, and I'm going to drop a couple of links here. I want to share. Let me see. Where are they? Some of you guys have already seen these. This is my lab update for the week. So, I wanted to, this has been something I've been wanting to do. I started on the first couple of these 6 months ago. Hopefully you can see those on my screen. So, APEC, right? I mean, we have a lot of folks that go from one conference to another, and they presented at several of these conferences. But APEC is the most recent in a long line of conferences. And this list isn't comprehensive, but one of the first real big ones was the High Frequency Gravity Wave Conference back in 2003. And that was like Bob Baker, Gary Stephenson, Paul Murad, many, many other, Martin Timar, I believe, went to that one. And Ning Li actually was the co-chair of that. So that was probably the first big one. So I started with that, and I wanted to do some promotional commemorative posters just to remember the contributions that these folks have made. I mean, again, APEC, we have had hundreds of scientists, engineers, and innovators, and these other conferences, when you add them in, they probably at least double it. ISNPS STAFE was an enormous conference. The Section F, the Symposium on New Frontiers and Future Concepts, that ran from 2004 to 2008. Paul Murad and Glenn Robertson, they were the chairs of that, right? And both of them are presented here. After that, there was the SPCIF conference, which Tony ran. Glenn Robertson ran that. And that, I was surprised once I dug into his meeting notes, that was just as big as STAFE, and that ran for a few more years. So it was a massive undertaking. Then there was Estes Park, right, which in some ways was kind of the inspiration for APEC. When you guys went to Estes Park and you said, wait a minute, this could be bigger from there. Then I wanted to put in Sarfati's Cortona 2023. This is the most recent. I used Cortona because I don't have information for his old ones. But Sarfati Science Seminars has been something that he has been doing for probably 20 years, off and on, right? It's not regular, it's not every year. But I at least wanted to put something up there to recognize that and recognize the people presented there. And then alt propulsion, of course, our very own APEC, which has been going strong for just about 3 years now. So we did have about a 6-month hiatus there, but we're rolling with things. So, I mean, it took me a while to kind of bring these together. If anybody wants these, I'm going to drop a link in. These are high res posters. You can actually print these at Costco. They're the 22 by 28 inch. They cost about $10 each, I think, to print. If you want these, if you don't, you can save them on your hard drive. These are full resolution PNG format files. They're free. It's just to commemorate the hard work of so many people, including you guys, including the people who are here right now. So, Jeremiah, go for it, sir.
Yeah, if I may, since we're giving credit to our predecessors and the giant shoulders that we stand upon, I also want to mention Tesla Tech and the Kofi conferences that came far before we had all this internet conferencing stuff going on. And I think that really, if we go back, they were some of the very originators, the very first to bring out the possibility of energy research that operated on different electrodynamics than what we have today, and in the advanced propulsion mechanisms that led to the possibility of things like SD Spark, Cortana, APEC, and all of these other conferences that came after.
Yeah, I would absolutely agree. The reason that I didn't get into those, well, number one, there are so many, right, that it would be like drinking from the fire hose. The other part too is a lot of those had a focus on energy, and so when I sat down, I was like, how can I try and focus this in on the propulsion side of things? But yeah, Jeremiah, you're absolutely right. I mean, Kofi and Tesla Tech, those go way back when, and they have had. They've covered this technology, right? So we definitely want to recognize them as well. I think that we're really lucky to have inherited such a tremendous legacy of work, right? And and that's that's the advantage of it. And when you think back, like for me, I started doing research in a college library with a card catalog, and it was a nightmare back then. And so for us to be able to go back through these conference videos and files, like Tesla Tech, for anybody who's not familiar with that, Steve Ellswick is starting to put up tons and tons of past conference footage online. So people don't have to relearn this from scratch. They can go back and learn from the work that's been done by others. So it's truly a blessing. So anyhow, that was my thing. But what I'm going to do is I'm going to paste a Google Drive link in there. You guys can download those at your leisure if you want. And if you want to come back to them later, just let me know. So I've got those, and I believe I have some APEC specific ones in there as well. And then, as Jeremiah requested, I'm going to drop our StreamYard link in there. Okay, I'll stop sharing. We've got everybody up on the screen. It's open discussion time. Dun, dun, dun. And the sound effects kicks it off. So,
just to note, we have had a lot of invasive and disruptive, perhaps not with the best interest participants that wanted to throw some things on there. So we're going to ask that you do go on camera so that we can see who you are before you are allowed in. And it's an unfortunate scenario, but because of the disruptions that have happened in the past, we're going to ask that you actually do get on cam. Even I have to put on a shirt and comb back my hair today. I got a little bit of leeway in the beginning because they know who I am, but honestly, like I shouldn't have. So please do have your cam ready and be prepared to show yourself and vet. And then come on in. Let's get this discussion going.
I got a question for Curtis from his stuff. So it looked like you were using Quaternions. Well, not you, the guy whose work you were referencing. He used Quaternions to model all of his unification. But correct me if I'm wrong, because I am no means an expert or even barely knowledgeable in this, but I thought that the non-associativity of the octonions was necessary to describe some of the particle generations, which, I mean, with the breadth of work that guy did, it looks like he probably addressed that at some point. But I was wondering if you could speak on that at all, as to Why did he limit himself just to stop at the Quaternions?
Yeah, so Mendel Sachs is his name, and he did quite a bit of work on particles. And the thing you got to realize about particle physics, and this is well known, is that what is measured usually is not the particles directly, right? The particles that are theorized, and that's why they have the whole how many sigmas is it? Because they're statistically correlating their model with what's observed, and what's observed is a shower of the mundane particles that we know. Okay, so how would I put this? So in terms of Octonians, I'm familiar with what you're talking about in terms of the symmetries and what can be proposed as an Octonian algebra. But for covariance, Octonians are not required. Now, it may be that at higher energies or there's more going on that could be something that is needed. I'm not convinced either way. And I would say that if it were the case, what I've been looking into actually specifically is geometric algebras, which are generalizations of quaternions, spinors, and those kind of mathematical objects. And I do know that there's people been working on. Has been work done on electrodynamics that is based on geometric algebras, and there's a movement to go back to using geometric algebras to teach physics at the beginning, so you don't have these strange, machinations you do in electromagnetism when you have magnetic fields and the curl and the divergence and having to put them together in weird ways. So I think Sachs was aware of the Octonians, but didn't feel like it was required from the axioms that the physics is coming out of. So think of it this way: basically, unless it's a thing where we know that okay, there's a phenomena that needs to be described, and we can't predict it. Is there a principle, something like okay, there's a symmetry, an algebraic symmetry that we need to apply? Then maybe we can look at it and say, okay, maybe the quaternions, maybe they're at this energy, but at much higher energy, the true symmetry is Octonians, and you break that symmetry at that higher energy, and it introduces more nonlinearity, so things get worse, even worse than they are. Bad enough with general relativity, but worse with this, and there's even worse thing. it's even harder to compute at that point. So, is there more there? Maybe, but there's with this theory, it's not doesn't rule it out, but doesn't necessarily need it.
Just one little add-on to that, but especially if you're trying to describe soliton evolution, I don't think quaternions quite do the full job for that, right? I think Octonians are required if you want to describe soliton evolution and how solitons, even though they're normally non-interacting, in certain scenarios they do, and that's where Octonians come into play, is describing those moments of intercept between colliding solitons.
Yeah, the way I like to think of it is like, okay, you look at ocean waves, right? You get the wave motion, but then sometimes something crests. So it's no longer, 2 dimensions is not enough, right? There's something that's outside of the function space. So,
well, if it's okay to jump in real quick, I wanted to ask Gary. Gary, welcome, sir. It has been quite a while since we've seen you.
Yes, can you hear me okay?
I can. Did you have, what did you have? We're an open discussion, so I'd say go for it.
Okay, yeah. I've been looking here lately, revisiting some of Fontana's work because there's some interest from some researchers in Canada about it. And so I went back and reviewed a paper published in '64 by Halpern and Laurent. Is anyone familiar with this paper? It's quite an interesting paper if you have a couple of minutes.
Yeah, absolutely, absolutely. And Curtis, I didn't mean to cut you guys off. Are you still working on things, or are you?
Oh, I was just going to say it's so there's potential that, like I said, that there might be a better algebra or a way of looking at it, which is maybe a categorification or some kind of topology that could expand the theory to include other effects that are not describable. But that being said, I don't know if with the way Sax's theory is, because it's quaternions kind of embedded in a tensor. So it is possible that maybe the solitons you're describing, maybe they can be described by that physics, because that mathematical structure is has a lot of nonlinearities, and so it's hard for me to say that is not allowed. I don't know.
Awesome. Okay, sorry about that. I'm busy self-distracting. I've got a coat and a heat lamp. I'm trying to juggle both, right? I'm like, yeah, go for it, Jeremiah.
Sorry, yeah. I just wanted to mention there are a few people that they may not have the cams set up, but they want to connect with a lot of the presenters here, some in particular that have really captivated the interest of specific audience members. So even if you can't get in, we can only host 10 with the current StreamYard plan, but there is a private chat in the back room where you should be able to make contact with some of these presenters at their own discretion, and hopefully you can go forward with your joint efforts and work from there. So please do come in, even if you can't get on the live here and visible, you should still be able to use that private chat in the back room.
Yeah, if it works. I've been getting notifications saying that we're at our limit, and
Yeah, I can jump off, Tim. I gotta go anyways.
Okay. Well, Jared, thank you, sir. Thank you.
Pleasure.
Sorry, can I do a lab update? I'll make room for somebody else after.
Okay, and so we'll have Gerald come in. I think.
Yeah, that would be awesome. Let's let Phil go, and then let's just prep for Gerald. Gerald did admit he has a cam issue. I can verify that.
Yeah. And
I've
Phil,
with him, but I know who he is, so I'll vet him.
What do you have for us, Phil? Mr. Bouchard.
Yeah, it's pretty awesome, and I'm glad to be part of the lab updates now. I'm done with the theory, but
there we go.
The theory really helped me predict the amount of weight loss that I'm gonna get by spinning a grinder. Actually, I just bought the grinder yesterday. I bought the battery pack today, and I ran it today. Yesterday in my finite theory group, I predicted I'm gonna lose 50 grams. Unfortunately, I cannot put the grinder on a vertical axis because I need to press the button, and when I press the button, it pushes down on the balance. So I need to put the button horizontally. So I need to flip in an angle like this. So anyway, I'll show you what happens. So there you go. It starts with the weight loss, and when I measure when I take my hand off, my hand away, to not to affect the weight, not to influence the weight, then I'm able to measure the weight alleviation, and it lasts until the disc starts spinning, and when it stops spinning, then the weights go back to the normal, and it's actually to the range. If the disc is actually inclined by 60 degrees, if you do the cosine of 60 degrees times 50 grams, then it's around 25 grams that I'm losing. I'm gonna play it again. See,
Okay.
that was around 20 grams weight loss. So yeah, I'm pretty happy about that. matches my predictions. And also, maybe I can show other videos proving that a magnetic field speeds up the plant growth. It's actually a time machine. That's what it is. Magnetic field speeds up time, and it speeds up the plant growth. I've got scientific evidence, and it's also speeding up. I have a scientific paper showing it's speeding up a photon. Photon travels faster. It redshifts and it travels faster. So it's pretty cool. So yeah, that's. I'm just gonna stop sharing that screen here and share.
Oh yeah, okay. Thanks, Phil. And then I don't want to forget Gary also, because Gary did have a paper to share with us.
Yeah, I just want to share the other. One sec. Yeah, I'm gonna share this paper because it's quick. So you see here that the last sentence before acknowledgement, the last sentence of the paragraph says, "Time goes faster for increasing magnetic field." So that's the conclusion of that paper, which is titled "Photon Redshift in a Magnetic Field," and it's already the mainstream already knows about it. Actually, I concluded these facts, and then I search around for existing scientific papers and YouTube videos to see if somebody already figured that out, and apparently yes. So I did not randomly found these papers. I found them based on my predictions.
Yeah. Do you want me to put that? I see that you have another page. Do you want me to put that one up?
Yes, please.
Okay.
This figure shows that under dark growth conditions, garden balsam plants only exhibited a marginal increase in growth rate when exposed to a static magnetic field. However,
Oh, and
the
Phil, is there a way to
magnetic
turn the
field was
volume off?
associated with an increased growth rate when the plants were grown under light. On day 3, the difference in height between the magnet-exposed plants and the controls was statistically significant.
Yeah, because I don't want
and
to
the
get any
differences
copyright
continued
strikes. That's
through
all.
day-
Oh yeah. So yeah. Anyway, so yeah, these are very important facts. Like, again, magnetic field is going to speed up the time rate, and yeah, these are very important. I did not randomly found these facts. I deduced them before finding these papers, and I debated also with Pablo on WhatsApp, so that to make sure these are scientific facts. So yeah, that's all I want to share. And
Okay. Well, Phil, thank you, man.
Yeah.
Let me without any further ado here. Let me go to Gary before he.
Did you want me to
disappears
show
on
that?
us.
Flash that
Yeah,
up?
Gary, do you want to put yours up? Do you want
Sure. I
to?
could share the screen here.
I'm just feeling guilty because I've interrupted you like 4 times. So.
This is the paper basically that Giorgio Fontana had based his gravitational laser on. It describes transitions that trigger gravitons. So these are transitions, electric shell transitions in the quantum states of the electrons, and it has a table in here that delineate all the important transitions. And so if we go to that table, it's table 1. It actually describes the exact pattern of radiation, both the electromagnetic multipolar radiation and the gravitational radiation. It's typically quadrupolar, but it can be higher order, so they call it multipolar. It's not dipolar like the electromagnetic radiation is. So they actually have equations for every single radiation pattern for every single transition, important transitions that emits either photons or gravitons. Of course, for us, we're interested in the graviton transitions. So we get down here and we see, oh, gravitational radiation transition for a J2, which is a double, a twofer on spin. So for a spin 2 transitions, you can get these gravitational radiation patterns. So I went through and did some notes on them, on these transitions, and traced it to Fontana's paper. Here he's showing the orbitals, K, L, and M, and he's looking at the transitions that if you force it from a 1s to a 3d, for instance, that gets, there's no photons allowed for that transition. It's only gravitons. So he's trying to force a graviton transition. How he does that is with a superconductor, with a pair of superconductors, a low temperature superconductor, which populates these S states, S waves, he calls them. And then he forces that transition into a D state, and that's a spin 2 transition, which is what you need for a graviton. So that is essentially, and it operates just on a DC current. There's a characteristic frequency that Josephson junctions have that they emit once a DC current is applied to them, and it's dependent upon the voltage and the geometry of the Josephson junction. But essentially, what you can do then, if you lay up a device, I don't know if he had it in this paper, the design. Yes, if you deposit a low temperature superconductor on a high temp superconductor, and for Josephson junction, typically there's an insulating, a very fine line of insulator allowed in the middle. If you deposit, for instance, lead on YBCO, that's the kind of device that can generate these gravitons directly. So you don't have to worry about the whole G over C to the 5 kind of losses here when you're trying to move matter or move energy, because here you're just generating the photons directly. So that led a group that I think want to remain nameless right now to look at running Fontana's experiment, and by building these things up, and they're talking to foundries now of either Josephson junctions, singular large Josephson junctions, or arrays of small ones. And the question is, can you arrange an array of Josephson junctions such that you can get a measurable gravitational wave out of this? Josephson junctions can also be used as receivers. They're typically used in this raw state as gamma ray receivers. And so if there's a gravitational wave in the gamma ray regime, it can force a transition in the opposite direction, and then they'll pick up this characteristic frequency of emission, and you bias the emitter one, and then you just run to an LNA, the receiver one, see if you can pick up that characteristic frequency of the gravitational wave. So that's it in a nutshell. We will see what the foundry says about layouts for, this is one potential layout of a gravitational wave antenna made of Josephson junctions. And you would have traces between them. And I'm playing with the spacing here to now decide what's a constructive interference type spacing. So I just thought I'd flash that up. More to come on this. If the foundry agrees to build these things, then we'll have more data, and hopefully, let's see if I can stop presenting here. Yeah, I'm not able to stop. Thank you. Yeah, we'll have more data on the building of these devices, and then the actual experimental outcome, in the months ahead.
Well, and Gary, you might not have noticed this, but Jeremiah has been jumping up and down in his chair for about 3 minutes now.
Oh, is that right?
So,
okay.
Yeah, he's been like, yay, yay. So Jeremiah,
he's got great diagrams, and this goes right back to some of the early experiments that I did on my first visit out there to the Falcon Labs. And Mark, Jeremy, Chris, and myself, we had all worked on trying to create some sort of pseudo-Josephson junction, knowing that it was a critical factor in receiving the phase transition between these different
different types, right.
And so it looked like you had magnesium oxide and another element. We were curious how you had created the Josephson junctions, because it's something that we'd struggled with a lot in the past. And we never really did solve it.
It's right. It's a difficult thing to solve, and you need a Josephson junction foundry to do it. And so we've been having discussions with Josephson junction foundries, and one in particular, I don't know that there's a there's going to be NDAs. I don't think they've been cut yet with this outfit, so I'm reluctant to call them out. But you really need a professional foundry that's used to building Josephson junctions to pull this off. Number one. Number two, they have to have a number of different deposition techniques because the lead is deposited in a different regime than the YBCO is growing. So you grow your YBCO first. You deposit a very, very thin layer of insulator. I just had magnesium oxide there as one potential solution. There are certainly other insulators you can look at. And Fontana claims that you don't even need that insulating layer. You can still get a Josephson junction tunneling, just raw, raw superconductor on superconductor. It's just the low temp versus the high temp variety. So we'll see. We're working with the foundries. Short versions, we're working with the foundries that know how to do it.
That's amazing. Of course, Gary, now after seeing this, my posters seem really lame.
No. Your posters are great.
I'm like, look, I made pretty posters. They're really cute. And you're like, yes, and we have this, we're getting a foundry. And no,
just to clarify, you're looking to make YCBO zinc oxide as a super insulator and then lead on top of that?
It might be magnesium oxide, but yeah, lead on top of that, right?
So you could generally directly generate gravitons then?
Well, the idea is to force a transition, a spin-2 transition to generate gravitons directly, right?
Do you think you could use that as a transmitter receiver? I mean, if you had two.
Yeah, that's the idea here, is that you're biasing that transmitting, that graviton transmitting Josephson junction, and when you hit it with a DC voltage, there's a characteristic frequency. And if you go to Wikipedia, you can look up what the characteristic. There's an equation that spells out very carefully what the characteristic frequency is of that Josephson junction. And my expectation is that it would modulate the gravitational wave at that same characteristic frequency. Then you can use another Josephson junction to force the opposite transition at the other end. See if you can pick up that frequency. Obviously, you're going to have Faraday cages to make sure you're not getting some EMI, right? So you rule out the EMI and you look for just gravitational wave coupling. That's the idea.
Is this a variation on the Podklanov superconductor impulse experiment?
Well, when these people first approached me, that was their intent. But these devices are so small. Typically, a foundry is working, down in the, microns or millimeters at most on wafers, and these are 4-inch wafers. And so the idea, you wouldn't be able to physically see anything. They're such small devices with such small outputs. But the idea is to trigger an effect somewhere else that is a gravitationally related effect. Yeah.
Now, so in terms of technologies for these, one thing, and this came up a while ago, in theory, if you could make this work, you could at least double the effective bandwidth that's currently available, right? Because you could do the same thing.
You would have an entirely different spectrum. You would have a gravitational wave spectrum at your disposal, which would presumably be regulated by the FCC, just like the electromagnetic spectrum.
But you could also use these for all sorts of measurement and detection as well, right? So.
Yeah, that's right. Well, so if this kind of scheme works, you can start doing astronomy with it. Look for. There's a whole spectrum of gravitational waves that haven't been looked at yet because nobody can build the detectors. So, for instance, for primordial gravitational waves, they're kind of left over from the Big Bang. They're ringing at potentially very high frequencies, or these primordial black holes when they burst. They emit these very high frequency gravitational waves. So there is this known spectrum, or predicted spectrum at least, of gravitational waves all the way up past the microwave range.
Yeah, it's just really exciting. It's really exciting.
Yeah, so we'll see what comes of it.
Yeah, no, well, Gary, thank you.
Sure.
That's super awesome. Well, yeah, stick around, and we're an open discussion, guys. I'm not sure what time you guys want to close this down today. Usually, probably around 5 or 6, something like that.
I believe Gerald is getting ready for a possibly short presentation, or may just be able to jump on for open discussion. I also wanted to mention, it looks like Tiziano is still in the background too.
Yeah.
So he has a question for Gary. And so please go ahead and type that, or if he's still in the back room, please let him in so we can ask. And I also wanted to mention,
if you guys want to, oh, that is Tiziano. Sorry about that. There we go. I'm sorry about that. I had it on the public chat, not the private chat. Tiziano, did you have questions? Do you have thoughts?
Hello. Sorry, I'm experiencing massive lags. Yes, I wanted to ask a question to Gary, if possible.
Sure, please go ahead. Go ahead. What's your question?
I remember looking at that stuff about 15 years ago, and I remember writing an email to Giorgio Fontana about this generation and capture of artificially generated gravitational waves. But so after him, to my knowledge, nobody ever continued that study, at least where he was in training.
Yeah, because his device,
So
as he described it,
where did you pick up with the?
What he published is he had a section in a book. That was one of the things I was showing that described these transitions and described a possible device. A book that was, I think, Eric Davis co-edited, if I remember right. And this was about 2011 or 2012.
Eric Davis.
Yeah, and it was a book on advanced propulsion schemes. And so Fontana had published.
Are you talking about the? Yeah, it's the one where I put it like in my second slide.
Maybe.
For 5 hours ago.
So I wasn't able
it's
to
like
join
the book, the only book.
Yeah. So but after that, nobody picked up on his work. The device, as he had described it, was not possible to build, and so it had to be shrunk down into a microscopic Josephson junctions in order to build it. I think that's what was holding everything up. Once we realized we could probably do a phased array, and we can make an array of small Josephson junctions, and that we might still be able to get an effect big enough to measure, that's when the work started moving forward again. But I have been in touch with Giorgio. Yeah, we stay in touch.
I'd like to stay in contact with you.
Sure. Let me. If you put your email in the chat, I can email you.
Okay, and I'm trying to see how to add Mark as a co-host, and Mark, it's not giving me any options for that.
I have a question.
Let me put my email in the chat.
And also another question.
Go ahead.
Sure.
Put mine too. The other question would be.
Here's my email. I see yours now. Okay, good.
Yeah. Well, and Gary, I wouldn't. Yeah. Don't.
What powers
okay.
would you expect from this kind of emission and reception of waves?
Yeah, that's a calculation.
In the milliwatt and in the microwatt.
It's going to be important. Yeah. So there's been a recent paper by a Bulgarian that calculated the powers. Let's see here. Let me see if I can find it in real time. So his name. Let's see. is Atanasov. A-T-A-N-A-S-O-V. Atanasov. He published a paper in 2018. Atanasov, yeah.
I know him.
Do you? Okay. He's been calculating the
Heard about
powers.
him.
Yeah, he's been calculating the powers. They look pretty crazy, right? They
Nice.
look big.
Good.
But that's for the device that we can't build. So I have to redo
I have
his
some
calculation for the smaller
works
devices.
of
I haven't
him
done it.
from 2018, 2019.
Yeah. And he recently did an update in 2023 this summer. And those are the power numbers I was going to revise for the smaller devices.
Looking at up now.
So you know him. That's interesting.
Okay.
I will send you his latest paper.
Thank you.
How's that?
Gary, I had a question for you.
Sure.
Thank you very much.
So how do we know it's a graviton and not some other unrelated to gravity electromagnetic effect?
Right. What I recommended is that the receiver be put in a different metal dewar than the transmitter. So they're both shielded by Faraday cages, so that we know that it's not an EMI electromagnetic effect. Otherwise, we won't be sure, right? Because we're running this Josephson junction, and it's going to be creating a characteristic frequency, and we might just be picking up that frequency if it wasn't shielded with the other Josephson junction, because these Josephson junctions are very sensitive to that.
Yeah, that's interesting. So so in this theory that I covered, the electromagnetic part of the theory includes more effects. It's kind of like if you look at there are other formulations of electromagnetism that include. I just want to mention Aharonov-Bohm effect, right?
Yes.
So that was shielded, and you still get a potential. You get something. So there's other.
You make a good point. I mean, who's to say? What's going to happen with this thing?
Yeah.
We maintain a lot of investigation to untangle these other novel EMI or like longitudinal waves. Nobody even looks at those longitudinal EM.
So I'm curious, when will the experiment be concluded in such that where you'll be able to publish and say, okay, we generated a signal and we received the signal, and here it is. And because people try to the theory side, if we could work out a prediction,
that's why I want to run the calculation on these smaller devices. And right now I'm waiting for the foundry to tell me what the size limits are.
I agree.
And when the foundry defines that, then I'll run the calc. But I haven't run the calc yet because I don't know how big we can make the devices. I want to make it as big as possible.
Right.
And then probably do an array of them until the wafers.
Is the foundry in the States?
Yeah, I don't know if I want to give any more hints. It's probably pretty easy to find this foundry.
Well, I used to work at ST Microelectronics when I was before our fab got moved to Singapore. So
really, oh yeah, yeah. Let me not answer until we get an NDA with them.
Yeah, that's fine.
Then I can release the whole press release.
But are you expecting that all that work would be done in a year or two?
Yeah, realistically, I think it's a year off because it's going to take them quite a while to do the fab, the layup, and the process design, even to do this layup, and it's going to be expensive. And I'm talking to these guys, and they're like, "It's going to cost a lot of money. Are you guys okay with that?" They're like, "Yeah, we're okay with it."
Yeah. Have you looked into the work of Ray Chow, by the way?
Yes. So yeah, these guys were energized by Ray Chow's work. Ray Chow, to a certain extent, was debunked by a guy named Robert Becker, not Baker, but Becker. Robert Becker was at Huntsville and published his master's thesis on Raymond Chow's work.
Yeah.
And if you look at that master's thesis, I just recently reread it. It's basically describes that Raymond Chow's approach wasn't sound and wasn't going to work, and that included the work of Ning Li. So that's
tried
when.
to talk, I was at UC Merced. I
connected.
was doing my PhD in physics there.
Oh, really?
Ray
Okay.
was one of the founding professors. So we were trying to talk him out of it, just so you know.
Yeah. So,
I mean,
if you read Becker's master's
the approach
thesis,
he was taking, we were trying to talk him out
yeah,
of that approach.
Becker's master's thesis examines 6 ways from Sunday, and at the end he's shaking his head saying, "No, it's not there." Unfortunately, we all wanted it to work, right? But
yeah.
Unless they've done something that they never came clean about in Ning Lee's lab, because it went dark for like 20 years, right? So who knows what was going on?
Yeah, and she died.
And then she died. Right? She got hit by a car and died. Yeah.
You were going to add something?
End of the story.
Yeah, sad ending to that story. Yeah. Okay, well, I will copy that email and get you that latest paper. Oops.
I think that the combination of something like Curtis is doing with this and with the kind of stuff that I'm doing will breathe new life into this kind of research, because I really think that the way in which we can go beyond what is now the accepted mainstream vanilla model of gravity, which is Einstein's field equation, is by really building an amplified, a bigger version of a particle, so at a human scale, because that's what matter really is. So you have this systems which are self-confined, they are cyclic. They of course they are described by complex numbers, or the evolution of complex numbers, which are spinors or quaternions or octonions. But one thing is to have the algebra of such mathematical objects, and one thing is to connect the algebra with actual physical referent. For example, I asked a question to Curtis in the chat. His nonlinear field equation, which of an electron, but the point is, okay, good, the mathematics is fine, it all works perfectly algebraically, but how does an electron look like? What does spin 1/2 mean exactly? We all do the algebra, we can all do the normal thing that we do in the courses in university, or we learn it by ourselves, but how do you make a particle? What are the design rules for making a proton, for making an electron? And I think that what happens with the macroscopic quantum systems is that we rescale the physics of fundamental particle to macroscopic scale. And we are just, so our theory, so the standard theory are not up to the task, because they do not provide the visual representation of what the world of microscopic particle is. So looking at the presentation of Curtis, I remember that I also encountered the works of Mendel Sachs previously, and I think I tell you this, it's like my approach to all of this, that as general relativity can be interpreted as geometry, but also as a user interface at continuous limit of something microscopic hiding underneath. Also, algebraic geometrical unified theory should be interpreted like this. So the relation that you may find with algebra and geometry and working with the symbology of Dirac equation, linear, non-linear, combining them with electromagnetism, combining them with gravity. That's like the user interface. It's like the surface. But I think that that's what's underneath it, which is the real physics that connects with laboratory.
Yeah. Well, Tiziano,
it was a little bit of a rant. It was a little bit of a rant. I don't know if I made myself clear. Or what do you think about this?
No, it's wonderful. If it's okay, I want to go to Gerald, because we're at the top of the hour, and he has an experiment that he's preparing. Let me do solo layout for Gerald right now. Okay. And hey, Gerald, I can.
Hello?
I'm going to mute myself out.
Awesome. Okay, so I'm going to show a couple of quick experiments here. What we have is a bifilar 750-foot wound vortex coil. The secondary is attached to this light right here. And these 4 ferrite cores are attached to these separate meters. Now, right now, it's not grounded, but I'm going to ground it. And I want you to watch these 2 meters right here. Now, they don't climb much. I'll give you that. Can you guys see the voltage coming up? I'm not sure if you could see that because I'm not getting a feedback on you guys, but 2.7.
What I've seen is, 2.7 on that 1 meter.
2.7, yes.
And 7 on this. It's not much, right? That's just connected to a ground. Now, this is what I use to power this. It's a wall plug, 28 volts. Okay? I'm going to put this right here. And I'm going to turn on just the power from the function generator. That's just the function generator. That's at 22,000 kilohertz, 40% duty cycle square wave. 20, 21, 14, 2.5. Now the 2.5 is because of this right here, which I will disconnect. And it's at 26. Now the thing is, these are all one wire. It goes directly from these ferrite cores to a half-wave rectifier, then to the ground. And that's how I'm getting this out. So now I'm going to shut off the function generator, and I'm going to plug in the 28 volts.
So just to clarify, in case people aren't familiar with your videos already, what you just showed there is that without the extra ground connection, you don't get the voltage gain across the one-wire connection with these other systems. But when you give it the ground reference, then all of a sudden you can pull electrons into and back out of the ground, and you're getting the voltage gain purely because you have this capacitive load to pull and push against. And this is a fundamental principle, not just with energy, but it's also been proposed many times that this can be used for repulsive forces, that we could push against the electric field of the Earth and its capacitive circuit between ground and the ionosphere to basically levitate a craft.
Thank you for that clarification. That's awesome, Jeremiah. Now I'm going to turn on the function generator, and this is just 1,000 hertz, 1 kilohertz. Now, I'm going to have to cover this light. We'll go Whopper style here. Can you guys see the meters? We have 185 volts here, 75 volts here, 115 here, and 110 here. Can you see the watt meter?
Just barely. Would you read us out the numbers?
I'll see if I could bring it up here. It says 27.63 volts, 5 to 7 watts. And I'm getting all of that.
I also wanted to mention that I was very impressed with your videos that you've been posting on your channel the other day, because you showed that with as little as 1.4 to 1.5 watts, you were able to produce the amount of light output that we would normally expect from an LED array like that. And that's not the most modern and new LED array by any means. You've had this for many years, but it looked like it should have taken at least 10 watts to pump into that array to produce the same level of light output. So either you found a really efficient way to run LEDs and get way more light at the same power input, or something else very interesting is going on here.
See, I was only set up for this because I was doing a video on showing the polarity of how if you turn the ferrite cores around, it stops producing voltage. And I wasn't set up for what I wanted to show. So if there's a future presentation spot open, I would love to show you guys this charging 4 to 6 batteries all on 27 volts.
Then let's get you set up for a future presentation. And at this point, for the remaining audience members, I'd like to point them towards your channel, WPG for Truth 2. And we should get a link there posted in the public chat so that they can check out your previous works, of which you have many.
I appreciate that. That would be awesome. Thank you.
Yeah, Gerald, just shoot me. You have my email address. Just shoot me an email. So our next scheduled session is November 25th. That's our next webinar, and then we have that open mic coming up too. And I can get the calendar. In fact, let me do that for anybody watching. So on the Alt Propulsion website, we have a calendar set up there, and I did that so that you guys would not miss a thing. So the next open mic is coming up on November 11th. That's obviously Saturday. It's 4 p.m. is when it starts. That's for Ad-Hoc, right? That's all comers. And then the next structured planned webinar where we schedule things out is on November 25th. And that is so far on the 25th. The only thing that we're talking about is Salvatore Pais and hopefully John Brandenburg. I'm working on getting them both here.
Well, whatever you decide, Tim, I'm just happy to be part of this. It's an amazing thing you guys put together, and I applaud all of you. You guys have done amazing work.
Well, thank you. And we're pushing hard to try and grow things and get more people involved and spread the word too. And Gerald, I would say definitely mention it in your network as well. I know Bernie mentions it, so it's. We're trying to create a community resource. That's
absolutely the goal. I'll spread it far and wide as possible, as best to my ability. But that's my presentation for today. So thank you very much.
Well, Gerald, thank you, sir.
Thanks for setting that up basically on the fly, impromptu at the last minute. Right. So none of that was planned, and you managed to get a lot, quite complicated setup in a very short order. So thanks for even what we've seen today. And we can't
that's why it's a mess. It would be much neater otherwise.
And guys, we should give a hand. We should give a hand to Gary and Gerald also for presenting. So Gary and Gerald, thank you both. Thank you both.
Thank you.
Yeah, I'm blown away by these conferences. We're making it work. We're making it work. Thank you, God. Thank you.
I've got to admit, Tim, you may have been right that this could be one of the best APEC conferences we've ever had.
Yeah.
The information revealed today was mind-blowing.
Yeah, I love it. We have a great mixture of theory and hands-on, and that's the whole goal, right? I mean, like I keep telling people, this is your guys' conference. We're just trying to get it out there to again create a library and create a resource. And after we wrap this up, I'll go back in. The same link that works from email will take you to the replay of the conference. And later tonight, I'm going to go in and put time markers in for each person's presentation, and then I'll update the page as well for that. So
sounds good.
I suppose this will be a good time to conclude. Thank you once again for not just all of our presenters today, but for all of you out there in the audience that watch this and are extremely interested in trying to make this the new reality for the future. Let's have that positive Star Trek universe that we've all seen, and let's do the best that we can as a species.
Well, Jeremiah, thank you very much for taking us out for today. Guys, this has been APEC for October 28th. Thank you, everyone. Thank you to our presenters. Again, absolutely amazing, amazing presentations. And thank you to our audience also. Thank you to everyone who's watching. Hopefully you can use this to advance your knowledge in your research, and we'll just keep moving everything along. Thanks again, guys, and have a wonderful evening.